Hello there, and welcome to Just About Earth, a quiet place where curiosity slows down, where questions are allowed to linger, and where science takes its time. Tonight, you don't need to solve anything, remember anything important, or rush toward an answer. You're here simply to listen, to unwind, and to follow a trail of ideas at a gentle pace. This channel exists for those moments when the world feels a little loud and the mind could use something steady and thoughtful to rest against. So wherever you are, however your day has been, you're welcome here. This time, we're turning our attention to something solid, heavy, and usually considered very straightforward: stone. Not the symbolic kind or the poetic kind, but real stone. Blocks so heavy that modern cranes struggle with them. Surfaces so smooth that they seem polished rather than broken. Joints so precise that even a thin blade struggles to slip between them. These are not isolated curiosities tucked away in one forgotten ruin. They appear again and again across the world, carved into mountainsides, stacked into walls, shaped into monuments that have quietly endured for thousands of years. What makes this strange is not that ancient people worked with stone. Humans have always done that. What unsettles modern engineers and archaeologists is how some of this stone appears to have been manipulated, not just moved, but shaped, fitted, and placed with a level of precision that seems difficult to reconcile with the tools we assume were available at the time. No hardened steel, no powered drills, no industrial saws. Often, not even clear evidence of extensive chiselling. Instead, we're left with stone that behaves in ways we don't expect stone to behave. Edges that curve where impact should fracture, surfaces that meet at complex angles without gaps, blocks that interlock as though they were softened, adjusted, and then allowed to harden again. This doesn't mean magic, it doesn't mean aliens, it doesn't mean anything supernatural at all. But it does suggest that there may be techniques, understandings, or processes that don't fit neatly into the simplified timelines we often repeat. Before we go any further, let me gently ask you something. Where are you listening from right now? Are you settled in for the night, perhaps with the lights low and the day finally behind you? Or are you listening during a quiet moment that feels briefly your own? And what time is it where you are? It's always interesting, isn't it, to think about how a conversation like this stretches across time zones, connecting people who are technically living in different parts of the same day. If you find this kind of slow, thoughtful exploration calming or quietly intriguing, you might consider liking the video or subscribing. It helps this space reach others who might be looking for something gentle to fall asleep to or something steady to think along with. There's no pressure, just an open invitation. Now, let's begin easing into the question itself. How did ancient people manipulate stone without the kinds of tools we rely on today? This is not a question about whether they were capable. They clearly were. The evidence stands, quite literally, in front of us. The question is about method, about process, about what was actually done step by step, hour by hour, generation by generation. When we say without tools, we don't mean without any tools at all. We mean without the kinds of tools that leave obvious familiar marks, without machines that rotate, grind, or vibrate at high speed, without alloys engineered for hardness, without the energy density we take for granted. Stone, under normal circumstances, resists shaping. Hit it too hard and it fractures. Apply uneven force and it splinters unpredictably. Try to cut it without a harder material and progress slows to a crawl. Modern stoneworking relies on brute force, multiplied by precision engineering. Ancient stonework in some cases seems to rely on something else entirely. Consider this quietly for a moment. If you were handed a block of granite weighing several tons, along with simple copper tools and stone hammers, how long would it take you to produce a surface that is flat to within fractions of a millimetre? Not roughly flat, not visually smooth, but geometrically precise. Now imagine doing that not once, but hundreds of times, and fitting those blocks together so tightly that they remain stable through earthquakes centuries later. This is where conventional explanations begin to feel strained. Archaeology often answers by extending timelines, Given enough time, enough labour and enough repetition, remarkable things can be achieved. And that is true. Time is a powerful tool. But even with generous timelines, certain features remain difficult to explain purely through abrasion and impact. There are stones that appear to have been shaped in ways that minimise stress fractures, as though the material responded plastically rather than brittly. There are curved internal corners that are hard to reach with straight tools. There are recessed cuts that seem uniform in depth across hard crystalline material. These aren't impossible, but they are unusual. What's more interesting is that these features appear across cultures that were separated by vast distances and had no known contact. South America, Egypt, parts of Asia. Each region has its own traditions, symbols and myths, yet the stonework shares certain quiet similarities, not in style, but in execution, in how the stone seems to have been persuaded rather than forced. One possibility is that ancient builders understood stone differently, not as an inert obstacle, but as a material with behaviours that could be influenced. Modern material science tells us that stone is not perfectly rigid. On microscopic scales, crystals vibrate, shift, and respond to stress. Under certain conditions, materials that appear solid can behave in unexpected ways. Heat does this, pressure does this, time does this, vibration does this too. This brings us to a delicate but important distinction. Saying that ancient people may have used sound, resonance, or chemical processes does not mean they had advanced technology in the modern sense. It means they may have had refined practical knowledge gained through long observation, experimentation, and oral tradition. Knowledge that didn't require writing equations or building engines, but relied on noticing what worked. Think about how humans learned to ferment food long before they understood microbiology, or how metalworking developed centuries before atomic theory. Practical knowledge often comes first. Explanation follows much later, if at all. Stone may have been approached the same way. Certain rocks respond differently to moisture. Some fracture cleanly when soaked and dried repeatedly. Others can be softened chemically through plant extracts or acidic compounds. Still others respond to sustained vibration by redistributing stress along crystal boundaries. None of this is speculative in isolation. What's speculative is whether these behaviours were deliberately harnessed at scale. When we look at ancient sites, we often look for tool marks that match our expectations. Straight grooves, repeated impact scars, parallel lines from saws. When we don't see them, we assume erosion has erased the evidence, or that simpler tools were used with extraordinary patience. But absence of familiar marks does not necessarily mean absence of technique. It may mean we are looking for the wrong signatures. There's also the matter of transport. Moving stone is not just about lifting, it's about friction, balance, and control. Ancient people clearly understood leverage. That much is undeniable. But some blocks were moved across uneven terrain, up slopes, or into positions that seem inefficient by brute force alone. This has led to experiments involving rolling stones, sledges, lubrication with water or oils, and carefully prepared pathways. Many of these methods work. Some work surprisingly well. Yet even when transport is explained, shaping and fitting remain stubborn questions. Another point worth considering is that knowledge doesn't always survive in written form. Skills transmitted through apprenticeship can vanish completely if the chain is broken. A technique used for centuries can disappear within a few generations if circumstances change. War, migration, climate shifts, or cultural collapse can erase practical knowledge without leaving clear records behind. This is especially true for knowledge that doesn't present itself as extraordinary at the time. Builders may not have thought of their methods as special. They were simply how things were done. There would have been no reason to document them carefully for future scholars who would one day find the results baffling. There's also a tendency, in modern storytelling, to frame ancient people as either primitive or impossibly advanced. Reality is usually less dramatic and more interesting. They were observant, adaptive, and deeply embedded in their environments. They worked slowly. They reused ideas. They refined processes over generations. And sometimes they arrived at solutions that look strange to us because our priorities and tools are different. As we continue, we'll look at specific examples, not to sensationalize them, but to examine them carefully. We'll consider stones that interlock without mortar, surfaces that seem machined but weren't, myths that may encode practical knowledge rather than fantasy, and modern experiments that attempt, cautiously, to replicate ancient results using non-industrial means. Nothing here requires belief in lost civilizations with impossible technology. It requires curiosity, patience, and a willingness to sit with uncertainty. Some questions may remain open. That's fine. Sleep, after all, doesn't demand closure. It allows thoughts to drift, connect loosely, and settle where they will. So for now, let the image of stone rest in your mind, heavy, silent, patient. It has outlasted empires and arguments alike, and somewhere within it, there may still be lessons we're only beginning to remember. There's a moment that happens to many people the first time they stand in front of certain ancient stone structures. It's subtle, easy to miss if you're distracted or rushing, but once it settles in, it's hard to shake. You look at the stone, you understand intellectually that it's solid, heavy, resistant, and yet something about it doesn't line up with that understanding. The edges don't behave the way you expect broken stone to behave. The surfaces don't tell the story your mind thinks they should. It's as if the material is quietly contradicting you, without drama, without explanation. Stone, as we usually encounter it, is stubborn. Drop it, and it cracks where it chooses, not where you want. Strike it, and it answers with jagged fractures and uneven breaks. Even with modern tools, shaping hard stone is loud, aggressive work. Sparks fly, bits shear off. Surfaces must be ground and reground to approach flatness. The process leaves scars, and those scars are usually easy to recognize. Yet in certain ancient sites, those scars are missing, or at least not where they should be. Instead, there are stones that appear to have flowed into place rather than being forced. Blocks that meet one another along complex curves rather than simple straight planes. Faces that are subtly convex or concave, shaped with intention rather than chance. And joints so tight that they challenge the idea that hammering and chiseling alone were responsible. This isn't about one monument or one culture. It's a pattern that appears quietly across continents. In Peru, walls built from massive irregular stones fit together so precisely that they've survived centuries of earthquakes without mortar. In Egypt, granite blocks weighing tens of tons show surfaces that are flat beyond what copper tools should reasonably achieve. In parts of Asia, stone pillars and chambers display internal curves and recesses that seem impractical to carve through straightforward impact. When people first encounter these examples, the reaction is often disbelief followed by dismissal. Surely we're exaggerating. Surely erosion smoothed things out. Surely the stones only look precise from a distance. But closer inspection tends to deepen the puzzle rather than resolve it. Measurement confirms the tight tolerances. Microscopic analysis sometimes reveals polishing patterns that don't align with known abrasive methods. And the stones themselves remain stubbornly uninterested in offering easy answers. One of the most intriguing aspects is how these stones handle stress. In modern engineering, stress distribution is carefully managed. Sharp internal corners are avoided because they concentrate force and lead to cracking. Smooth transitions are preferred. Curves distribute pressure more evenly. This is common knowledge today, backed by equations and simulations, but many ancient stones appear to embody this same logic without written theory. Instead of square corners where blocks meet, you sometimes find subtly rounded interfaces. Instead of flat planes slamming together, there are gently undulating contact surfaces. These choices don't make construction easier. In fact, they make brute force carving significantly harder. They do, however, make structures more resilient. This raises an uncomfortable question. Why would builders working with limited tools choose methods that demand greater control and precision unless they had a way to achieve that control more efficiently than we assume? Another point worth lingering on is consistency. Natural erosion tends to be uneven. Wind, water, and time leave chaotic signatures. Yet many ancient stones show consistency across surfaces that were once hidden from the elements. Inner faces of walls, protected joints, areas shielded from centuries of weather still display the same smoothness and intentional shaping. This suggests the features were present from the beginning, not the result of slow environmental polishing. Then there's the issue of hardness. Granite, diorite, basalt, and similar stones rank high on the Mohs hardness scale. Copper, which is often cited as the primary ancient metal tool material, is significantly softer. It can be used with abrasives, yes, but the process is slow and leaves characteristic patterns. Those patterns aren't always present where expected. It's important here to be careful. None of this proves that ancient people had secret machines or advanced technology hidden from history. What it does suggest is that the relationship between tool, material, and method may have been different. Perhaps stone wasn't always treated as something to be cut aggressively. Perhaps it was treated as something to be encouraged, guided, or gradually altered. Modern material science tells us that stone is not as static as it appears. On a microscopic level, crystals are arranged in lattices. Stress causes those lattices to shift. Heat changes their behavior. Moisture can weaken bonds. Chemical exposure can alter surfaces. Over time, these effects accumulate. In laboratories, stone can be softened, etched, or reshaped without striking it at all. Ancient people may not have described these processes in modern terms, but they didn't need to. They only needed to notice patterns. If a certain plant extract made stone surfaces easier to work, that knowledge would be passed on. If soaking a block before shaping reduced cracking, that would become standard practice. If rhythmic tapping at certain frequencies caused fractures to propagate predictably, that rhythm would be learned and repeated. There's a tendency today to assume that if something wasn't written down, it wasn't known. But for most of human history, writing was rare and reserved for administration, ritual, or power. Technical knowledge lived in hands, not texts. It was transmitted through watching, doing, correcting, and repeating. A master builder didn't need to explain why something worked. The apprentice only needed to see that it did. This makes the loss of such knowledge surprisingly easy. Break the chain of apprenticeship and the technique vanishes. A generation grows up without learning the subtle methods, and suddenly all that remains are the finished stones, silent and unhelpful. When stone refuses to behave like stone, it forces us to confront our assumptions. We tend to think of technological progress as linear, always moving forward. But history is messier. Knowledge can advance in one direction while retreating in another. Skills can be refined and then forgotten. Techniques suited to one cultural context may become irrelevant in another and quietly disappear. Another aspect that complicates matters is scale. Many ancient structures involve not just a few oddly shaped stones, but hundreds or thousands of them. Precision repeated at scale suggests process, not accident. A single well-fitted joint might be luck. An entire wall of them implies methodical repetition. There's also evidence that shaping occurred after stones were placed, not before. In some sites, blocks appear to have been roughly positioned and then adjusted in situ, their faces refined to fit neighbouring stones perfectly. This would be extremely difficult with hard stone using impact tools, especially once the block is constrained by its surroundings. This has led some researchers to consider whether stone might have been temporarily softened or made more workable. Not melted, not liquefied, but altered just enough to allow fine shaping. Certain chemical reactions can do this at surfaces. Acids can etch minerals. Alkalis can weaken crystalline bonds. Even prolonged exposure to heat combined with moisture can change material properties. There are ancient accounts, often dismissed as myth, that describe stone being treated with substances derived from plants. In some stories, builders sing to the stone. That detail is usually mocked or ignored, but sound is vibration, and vibration does affect matter. Resonance can amplify small forces. Sustained vibration can reduce friction and alter stress distribution. Modern experiments with ultrasonic vibration show that materials can behave differently under resonant conditions. Cutting becomes easier. Cracking follows predictable paths. Again, this doesn't require advanced electronics to be discovered accidentally. It requires noticing that certain sounds, rhythms, or repeated motions produce better results. There's also the possibility that what we interpret as tool absence is really tool unfamiliarity. Tools made from organic materials like wood, bone, or plant fibre rarely survive. Even softer stone tools can erode beyond recognition. What remains are the results, not the means. And yet, even accounting for lost tools, some features still feel oddly deliberate. Take the way certain stones bulge slightly outward, creating a subtle cushion effect. This isn't decorative, it improves load distribution. Or consider how some joints zigzag rather than run straight, increasing surface contact and stability. These choices reflect an understanding of material behaviour that goes beyond simple stacking. What's particularly striking is how calm these structures feel. They don't look forced, they don't show signs of struggle, there's no visual sense of violence against the material. Instead, there's a quiet cooperation between human intention and geological substance. This challenges a modern mindset that equates progress with domination over nature. Ancient builders may have been less interested in conquering stone and more interested in working alongside its tendencies. That kind of relationship produces different results, and it leaves different evidence. As you sit with this idea, it's worth letting go of the need for a single answer. There may not have been one method. Different cultures may have arrived at similar solutions through different paths. Some techniques may have been local, others widespread. Some may have involved chemistry, others mechanics, others patient incremental shaping. What unites them is that they don't fit neatly into a story of crude tools and endless labour. They suggest nuance, experimentation, a sensitivity to material behaviour that we don't often cultivate today because our machines do that work for us. Stone refusing to behave like stone isn't an accusation against history, it's an invitation to look more closely, to question comfortably held assumptions, and to accept that human ingenuity has always been broader than the stories we tell about it. At some point, the conversation about ancient stonework stops being about size and starts being about precision. Enormous blocks are impressive, yes, but size alone can be explained with enough people, enough leverage, and enough time. Precision is harder to dismiss. Precision demands control. It implies repeatability. It suggests that the builders were not merely strong or patient, but accurate, consistently so, across projects that lasted decades or centuries. When people talk about ancient masonry, they often picture rough walls, uneven surfaces, stones stacked with visible gaps and filled with rubble or mortar. And in many places that picture is accurate. But there are other sites where the stonework tells a very different story. Walls where each block meets the next so cleanly that the joint almost disappears. Corners where angles align with a care that feels deliberate rather than incidental. Surfaces that remain flat and true even after thousands of years of environmental stress. What makes this puzzling is not just that such precision exists, but that it exists in contexts where the usual explanations feel insufficient. These stones were not cut in modern factories. They were not measured with laser levels or machined with diamond-tipped blades. And yet, the results sometimes rival or exceed what we would expect from far more recent construction. Take, for example, the simple act of fitting two stones together. In modern masonry, this often involves cutting stones to standardized shapes and relying on mortar to fill small imperfections. Mortar forgives error. It absorbs irregularity. It allows speed. Ancient precision masonry often avoids mortar altogether. Instead, it relies on direct stone-to-stone contact. This removes any margin for sloppiness. If the surfaces do not match, the structure fails. What's striking is how often the surfaces do match, not just along straight edges, but along complex irregular boundaries. Some stones interlock with neighbours along curves and angles that would be difficult to plan on paper, let alone execute repeatedly. Each stone appears custom-fitted, shaped to meet its specific neighbours rather than cut to a universal template. This kind of fitting requires more than measuring length and width. It requires understanding how surfaces meet in 3 dimensions. It requires anticipating how a stone will settle under its own weight and under the weight of stones above it. It requires adjusting for minute irregularities that only become apparent when stones are brought together. In modern practice, this level of fitting is usually achieved through iterative testing with precision instruments. Stones are placed, measured, removed, adjusted, and placed again. This process is time-consuming even with modern tools. The question is not whether ancient builders could have done this, but why they would choose to do so in this way, consistently, across large structures. One answer often given is durability, and it's a good one. Precision-fitted stone structures are remarkably resilient. Without mortar to crack or degrade, the stones can move slightly during seismic activity and then settle back into place. This flexibility allows walls to survive earthquakes that would destroy more rigid constructions. But durability alone doesn't explain everything. Precision of this kind also requires a way to achieve flatness and smoothness at scales that are difficult to judge by eye. Human vision is good, but it has limits. Achieving a surface that deviates by less than a millimetre across a large stone face requires either extraordinary skill developed over a lifetime or some form of reference system that goes beyond simple visual alignment. Some ancient builders clearly had reference systems. Plumb bobs, water levels, and straight edges are well documented. These tools are effective and shouldn't be underestimated. A water level, for example, naturally finds true horizontal regardless of distance. A plumb line defines vertical with remarkable accuracy. With patience, these tools can produce impressive results. Still, certain features push the limits of what these tools alone comfortably explain. For instance, stones with slightly convex faces that meet neighbouring stones along continuous contact surfaces. The convexity is subtle, often invisible without careful measurement, but it serves a structural purpose. It ensures that contact pressure is distributed toward the centre of the stone rather than concentrated at edges. This reduces cracking and improves long-term stability. Creating such convex surfaces intentionally requires more than flattening. It requires shaping with an understanding of load behaviour. Modern engineers learn this through formal study. Ancient builders would have learned it through observation and experience, but that experience would need to be extensive and systematic. Another puzzling feature is symmetry across large distances. In some ancient walls, stones on opposite sides mirror each other in shape and placement, even when separated by tens of metres. This suggests planning beyond the immediate stone. It implies that builders had a mental or physical model of the entire structure, not just the piece in front of them. This kind of planning becomes even more impressive when stones are irregular rather than rectangular. Irregular stones don't naturally align. They must be made to align. Each adjustment to one stone affects the placement of the next. This creates a cascading dependency where early decisions constrain later ones. Maintaining precision across such dependencies is challenging under any circumstances. There's also the matter of surface finish. Many ancient stones exhibit finishes that are smooth but not glossy, uniform but not obviously polished. Tool marks, when present, are often faint and inconsistent with known tool profiles. In some cases, microscopic analysis reveals patterns that suggest rubbing rather than cutting, pressure rather than impact. Rubbing stone against stone with abrasive material is a known technique. It works, but it is slow, especially on hard rock. Doing this across thousands of stones would require not just time, but an organisational commitment to quality that goes beyond what we often assume of ancient labour systems. This brings us to an uncomfortable but necessary realisation. We tend to underestimate ancient specialisation. We imagine large workforces of unskilled labourers following simple instructions, but precision masonry suggests the presence of highly skilled individuals whose primary role was shaping, fitting and finishing stone. These were not interchangeable workers, they were experts. Expertise changes what is possible. A master stoneworker develops an intuitive sense of material behaviour. They feel resistance. They notice subtle changes in sound and vibration. They learn how much pressure is too much. Over decades, this embodied knowledge becomes remarkably precise, even without formal measurement. That said, expertise alone does not eliminate all puzzles. Some stones appear to have been shaped in ways that minimise waste and maximise fit efficiency. Instead of cutting large amounts of material away, builders seem to have adjusted surfaces incrementally, preserving mass and strength. This suggests a method that favoured surface modification over bulk removal. In modern terms, this resembles finishing rather than carving. Finishing works with the existing form. Carving imposes a new one. Finishing stone to fit another stone requires responsiveness. It requires testing and feedback. It's a dialogue between surfaces. Evidence for this can be seen in stones that bear matching irregularities. A small protrusion on one stone corresponds exactly to a recess on its neighbour. This is not something that happens by chance. It implies that stones were brought together, marked or felt against one another, and then adjusted accordingly. How are these adjustments made? Repeatedly lifting and lowering multi-ton stones would be inefficient and risky. It's possible that stones were adjusted while partially supported, allowing fine shaping without full removal. It's also possible that shaping occurred after placement with surfaces refined in situ. Shaping in situ raises further questions. Access becomes limited. Visibility is reduced. And yet, the precision remains. This suggests methods that did not rely solely on direct visual inspection. Tactile feedback, sound, and even smell can convey information about material removal. Experienced craftspeople use all of these senses. Another layer of the puzzle lies in the consistency of results across different types of stone. Limestone behaves differently from granite. Basalt fractures differently from sandstone. Yet similar levels of precision appear across these materials. This implies adaptable methods rather than a single rigid technique. Adaptability is a hallmark of practical knowledge. Instead of forcing one approach everywhere, builders adjust based on local conditions. They learn which stones respond well to which treatments. Over time, this produces a body of knowledge that is both flexible and reliable. What complicates our understanding today is that we tend to look for written explanations or preserved tools. When we don't find them, we assume the knowledge didn't exist. But practical systems often leave little trace beyond their results. Once the structure is complete, the scaffolding comes down, the temporary tools wear out, and the techniques live only in memory. When that memory is lost, we're left staring at stone and asking how. There's also a cultural factor at play. Precision masonry often appears in contexts associated with ritual, authority, or long-term significance. These were not throwaway buildings. They were meant to endure. That intention alone justifies a higher investment of time and care. In societies where time was not monetized in the modern sense, where projects spanned generations, patience was a resource. Precision could be pursued without the pressure of deadlines. A wall could take years to perfect because its value was measured in centuries. This long view changes priorities. Instead of asking how fast something can be built, the question becomes how well. Instead of minimizing labor, the goal becomes maximizing permanence. The puzzling precision of ancient masonry, then, may not be puzzling at all when viewed through the lens of different values. What seems excessive to us may have been sensible to them. What seems inefficient may have been optimal within their social and economic systems. Still, certain technical aspects remain genuinely challenging to explain fully. Not impossible, but demanding. They push us to reconsider the sophistication of ancient craftsmanship and the range of techniques that may have existed. As we continue, attention will shift from the results to the process, from what we see to what might have been done, from finished walls to the quiet actions repeated day after day that made those walls possible. Precision does not appear suddenly. It accumulates. It is the product of countless small decisions made correctly over time, and stone, when treated with patience and understanding, can respond in ways that feel surprising only because we no longer work with it that way. There is a difference between making something fit and forcing it to fit. You can feel that difference even without knowing anything about stonework. Think of a drawer that slides smoothly into place versus one that has to be shoved, tilted, and coaxed shut. Both end up closed, but only one feels right. Ancient precision stonework often gives that second feeling of inevitability, as though the stones arrived at their positions naturally, not through struggle, but through understanding. When you look closely at certain ancient walls, what stands out is not power, but restraint. The stones are not stacked in simple layers. They are not uniform blocks cut to identical dimensions. Instead, each stone seems to have its own shape, its own personality, and yet it belongs exactly where it is. Remove one, and the surrounding stones lose context, like words pulled from a sentence. This is especially clear in walls where stones interlock along winding, irregular boundaries. The joints don't follow straight vertical or horizontal lines. They curve, dip, rise, and twist. At first glance, this looks chaotic, but the chaos is controlled. The shapes are deliberate. Each joint increases surface contact, spreading load and preventing movement. The stones hold each other in place, not through weight alone, but through geometry. Force-based construction tends to favour simplicity. Straight cuts are faster. Flat faces are easier to achieve. Rectangular blocks stack neatly and predictably. If ancient builders were relying primarily on brute force, we would expect to see more of that. And in many places we do. But in the sites we're considering here, something else is happening. The stones are not optimised for speed. They are optimised for fit. Fit requires anticipation. You cannot shape one stone in isolation and expect it to fit perfectly later unless you already know what it will meet. This suggests a process where stones were shaped in relationship to one another, a dialogue rather than a monologue. One stone informs the next. Adjustments are made not according to an abstract plan, but according to immediate feedback. This kind of process is familiar to craftspeople. Woodworkers fitting joints by hand don't rely solely on rulers. They test, feel resistance, remove tiny amounts of material, and test again. The goal is not to remove as much material as possible, but as little as necessary. The joint improves gradually, almost invisibly, until suddenly it is right. Translating that approach to stone, especially hard stone, is not trivial. But the logic is the same. Remove too much and the stone is ruined. Apply uneven force and it cracks. The safest approach is incremental, controlled, responsive. One of the most telling signs of this approach is the presence of matching irregularities. A slight bump on one stone corresponds exactly to a hollow on its neighbour. These are not generic shapes, they are paired features. That pairing implies that the stones were brought together, their contact points identified, and then modified accordingly. This process would be difficult if stones were shaped entirely at the quarry and then transported finished. It suggests that at least some shaping occurred at the construction site, where stones could be tested against each other directly. This also explains why some stones appear to have been shaped on multiple faces only after placement, not before. There is evidence in certain sites that stones were set roughly into position and then refined. Surfaces that face inward, hidden from view, are often just as carefully shaped as visible ones. That would be unnecessary if appearance were the primary concern. But if fit and stability were the priority, then every contact surface matters. Another detail that supports this idea is the way stones sometimes seem to cradle each other. Instead of flat faces pressing together, there are subtle curves. A stone may rest into a shallow basin carved into its neighbour. This increases contact area and reduces point stress. It also makes shifting more difficult, because movement would require lifting as well as sliding. Creating such complementary shapes requires foresight and patience. It also requires a way to judge curvature without modern measuring devices. That judgment likely came from repeated tactile testing. Hands rather than eyes would have been the primary sensors. Pressure, friction, and balance communicate information that sight alone cannot. Force-based construction often leaves visible evidence: chisel marks, impact scars, fracture lines. In many ancient precision stones, these are minimal or absent on finished surfaces. That doesn't mean tools weren't used. It means they were used carefully, sparingly, and perhaps in combination with other methods. One possibility is that surfaces were first rough-shaped and then gradually refined through rubbing and abrasion. Stone against stone, with sand or other abrasives in between, can produce surprisingly smooth and accurate surfaces. This method is slow, but it offers excellent control. Material removal happens evenly. Sharp edges are avoided. Stress is distributed. Slow methods change how one thinks about construction. When progress is incremental, there is time to correct mistakes early. There is time to test assumptions. There is less incentive to rush or to force outcomes. Over long periods, this leads to refinement rather than improvisation. Another factor worth considering is sequencing. Stones may not have been shaped in random order. Certain key stones may have been placed first, establishing reference points. Subsequent stones would then be shaped to fit those anchors. This reduces cumulative error and allows complex forms to emerge coherently. This approach contrasts with modular construction, where standardized units are produced independently and then assembled. Modular systems favor efficiency and scale. Fitted systems favor integration and resilience. Ancient precision masonry clearly belongs to the second category. What's especially interesting is that this approach appears repeatedly in places where seismic activity is common. Earthquakes expose weaknesses in rigid structures. Walls built from uniform blocks and stiff mortar crack and collapse. Walls built from interlocking stones with no mortar can shift, absorb energy, and settle back into place. This suggests that the builders understood, at least intuitively, how structures behave under stress. They weren't just stacking stones, they were designing systems. Design, in this context, doesn't require drawings or calculations, it requires pattern recognition. Builders would have observed which structures survived and which failed. Over generations, those observations would shape practice. Stones that fit well would be preferred. Techniques that produce durable results would be retained. This kind of evolutionary knowledge doesn't leave blueprints behind. It leaves outcomes, walls that still stand, stones that still fit. There's also a psychological dimension to this way of working. Force-based methods tend to produce a sense of opposition. The material is an obstacle. It must be overcome. Fit-based methods produce cooperation. The material is a partner. It must be understood. This mindset affects choices at every level: how much pressure to apply, when to stop removing material, how to respond to resistance. It encourages listening rather than insisting. Some ancient accounts, often dismissed as metaphorical, describe builders listening to stone. This doesn't have to be mystical. Stone produces sound when struck or rubbed. Changes in pitch can indicate internal flaws. Changes in vibration can signal stress. Experienced workers can learn to interpret these cues. Even today, some craftspeople tap materials and listen. Carpenters listen to wood. Potters listen to clay. Mechanics listen to engines. Sound carries information. In a quiet environment, subtle differences become noticeable. There is also evidence that stones were not always treated dry. Water can play a role in shaping. Wet abrasives cut more evenly. Moisture reduces dust and heat. Repeated wetting and drying can weaken surface bonds in certain stones, making fine adjustments easier. None of this requires advanced technology. It requires time, attention, and a willingness to work slowly. Another intriguing detail is that stones that fit exceptionally well often show minimal signs of correction. There are few patches, few filled mistakes. This suggests that errors were caught early, not after the fact. It also suggests that builders had a good sense of when a stone was ready. Knowing when to stop is a skill. Remove too little, and the stone won't fit. Remove too much, and it never will. The margin is small. Consistently hitting that margin implies training and experience. This brings us back to the idea of specialized roles. Not everyone on a construction site would have been shaping stones. Most would have been moving, supporting, preparing, and assisting. A smaller group would have been responsible for fitting. These individuals would have carried the knowledge. Over time, their techniques would become tradition, not written down but embodied, passed from hand to hand. When those traditions ended, the knowledge ended with them. Looking at these stones now, it's tempting to project mystery onto them. But there is another possibility that is both less dramatic and more profound. The stones fit because people learned how to make them fit, through patience, through observation, through a relationship with material that prioritized understanding over dominance. This doesn't mean every question is answered. There are still details that challenge replication. There are still features that remain difficult to explain fully. But the overall pattern points toward a philosophy of construction that is fundamentally different from modern industrial approaches. Instead of asking how much force is needed, the question becomes how little. Instead of asking how fast, the question becomes how well. Instead of imposing shape, the goal becomes revealing it. Stone does not always need to be conquered to be shaped. Sometimes it only needs to be understood well enough to be guided into place, where it settles not because it is trapped, but because it belongs. Long before steel blades, before electric motors, before the steady hum of machines doing the work for us, people were already shaping the physical world with care and intention. It's easy, from a modern perspective, to imagine that without advanced tools, progress must have been slow, crude, and full of trial and error. But that assumption quietly overlooks something important. Complexity does not always arrive last. Sometimes it arrives early, settles in, and is later abandoned when faster, cheaper, or more convenient methods take its place. When we think of ancient construction, we often picture a gradual climb. First stone hammers, then copper tools, then bronze, then iron, and eventually steel. Each step supposedly cleaner, sharper, more effective. But history does not always move in neat steps like that. In some cases, the earliest methods are not the most primitive. They are simply different, shaped by priorities that no longer guide us. Before metal was common, stone was not treated as an enemy. It was not something to be aggressively cut into submission. Without hard blades to force quick results, builders had little incentive to rush. Speed was not the primary goal. Reliability was. Longevity was. Predictability mattered more than efficiency. Working without metal imposes discipline. You cannot simply strike harder to fix a mistake. You cannot grind away large amounts of material without consequences. Every action carries risk. That kind of environment encourages restraint and planning. It encourages methods that minimize error rather than correct it after the fact. This is where the idea of before mistakes begins to make sense. Modern construction tolerates mistakes because machines allow us to fix them. Cut too much, and you weld or patch. Drill in the wrong place, and you drill again. Concrete cracks, and you reinforce it. Ancient builders did not have that luxury. A mistake in a massive stone could ruin weeks or months of work. So the system evolved to prevent mistakes rather than repair them. One way to do that is to work slowly. Another is to rely on feedback rather than force. If you remove material only in small increments, you can stop before irreversible damage occurs. If you test fit constantly, errors reveal themselves early. If you shape gradually, the stone itself guides the process. This approach contrasts sharply with industrial logic. Machines are designed to remove material quickly. They assume excess. They assume waste. They assume correction will come later. Ancient stonework, in many of its most refined forms, assumes the opposite. It assumes scarcity, permanence, and consequence. Before machines, there was also no separation between design and execution. Today, an engineer designs and a machine executes. In ancient contexts, the person shaping the stone was often the same person deciding how it should be shaped. This collapses feedback loops. Decisions are informed instantly by material response. There is no abstraction gap. That matters more than it sounds like it should. Many modern errors occur because design assumes ideal conditions. Real materials are not ideal. Ancient builders could not afford to ignore that. They had to listen to what the stone was doing in real time. Before metal, many tools were softer than the stone itself. That forces a fundamental shift in strategy. You cannot dominate a harder material with a softer one. Instead, you must exploit weaknesses, natural fracture lines, grain orientation, variations in density, environmental effects. Stone is not uniform. Even within a single block, properties change. Ancient quarrying techniques often took advantage of this. Builders selected stone carefully, not just for size but for behaviour. Some stones were chosen because they fractured predictably, others because they resisted fracture. That choice determined how they would later be shaped. Without machines, repetition also meant something different. Today, repetition is automated. The same action is performed identically thousands of times. Ancient repetition was embodied. Each repetition was similar but never identical. That variability can be a strength rather than a weakness when working with natural materials. Instead of forcing stone into standardized shapes, ancient builders often allowed variation and then accommodated it. That accommodation shows up in fitted masonry, where stones are shaped to one another rather than to an abstract ideal. Variation is absorbed rather than eliminated. This approach dramatically reduces the risk of cumulative error. In a standardized system, a small mistake repeated many times becomes a large problem. In an adaptive system, each piece corrects for the last. Another important point is that without machines, noise levels were lower. This may sound trivial, but it matters. A quieter working environment makes subtle sensory feedback possible. Sound, vibration, resistance, and even smell can inform the worker. Machines drown that information out. Stone emits sound when struck, rubbed, or stressed. The pitch and tone change depending on internal structure. Experienced workers can detect cracks before they become visible. They can hear when material is close to failure. That kind of sensitivity is only possible in an environment where attention is not overwhelmed. Before metal tools became widespread, stoneworking also relied heavily on collective knowledge. Not written manuals, but shared practices. Young workers learned by watching, not by reading. Correction was immediate and physical. A master could stop an action mid-motion. Knowledge was reinforced through muscle memory. This kind of learning produces consistency of outcome, even when methods are not explicitly articulated. It also makes that knowledge fragile. Remove the context, and it disappears quickly. There is evidence that in some regions, later builders with access to metal tools produced cruder stonework than their predecessors. This is counterintuitive if we assume better tools always produce better results. But better tools can encourage different priorities. Speed over fit, quantity over quality. Metal tools allow you to force outcomes. They make it easier to recover from errors. That reduces the incentive to avoid them in the first place. Over time, systems optimize for speed replace systems optimize for precision. This doesn't mean later builders were less skilled. It means they were solving a different problem. Before machines, construction was slow enough that decisions mattered deeply. A wall might take a lifetime to complete. A structure might span generations. In that context, investing extraordinary effort into getting things right early makes sense. Before mistakes became fixable, they had to be prevented. Another factor often overlooked is energy. Machines concentrate energy. A modern saw delivers enormous localized force. Ancient methods distributed energy over time, rubbing, tapping, vibrating, soaking. These methods act gently but persistently. Over long periods, they can produce significant change with minimal risk of catastrophic failure. Distributed energy also respects material limits. Instead of exceeding stress thresholds and causing fractures, it stays below them, gradually reshaping surfaces without breaking them. This approach aligns with what we see in many ancient stones. Surfaces that appear worn rather than cut, edges that are softened rather than sharp, transitions that are gradual rather than abrupt. There is also less incentive, in pre-machine contexts, to hide process. Today, finishes often conceal how something was made. Ancient finishes often reveal it. The subtle irregularities are not flaws, they are signatures of method. Looking at these stones with modern expectations can be misleading. We expect uniformity because machines produce uniformity. Ancient builders may not have valued that. They valued stability, fit, and endurance. Before metal, even measuring systems were different. Units were often based on the body. Hand spans, foot lengths, arm reaches. These units are imprecise by modern standards, but they are consistent within a community. They also scale naturally with human interaction. When stones are shaped and placed by people using bodily reference rather than abstract units, the result often feels organic rather than mechanical. That doesn't mean it lacks precision, it means the precision is contextual. Before machines, alignment was achieved through gravity, plumb lines, hanging weights, water surfaces. These methods are remarkably accurate because they rely on physical laws rather than manufactured calibration. They do not drift, they do not wear out. Using gravity as a reference anchors construction to the environment itself. Vertical is not defined by a device, it is defined by the earth. Horizontal is not an assumption, it is discovered. This grounding may help explain why ancient structures often feel stable and settled, as though they belong to the landscape rather than imposing themselves upon it. Before metal, maintenance was also different. You could not easily replace parts. Structures had to be robust enough to endure without constant intervention. That encourages redundancy, interlocking systems, self-stabilizing forms. This shows up again in fitted stonework. Each stone supports and is supported. Load paths are shared. Failure of one element does not necessarily propagate. Modern structures often rely on fewer, stronger elements. Ancient structures often rely on many moderately strong ones working together. Another subtle point is cultural attitude toward time. In many ancient societies, time was cyclical rather than linear. Projects were not always expected to finish quickly. Seasonal rhythms governed work. Construction paused and resumed naturally. This reduces pressure. It allows reassessment. It allows mistakes to be caught not because someone is rushing to meet a deadline, but because there is time to notice. When you combine slow methods, attentive feedback, adaptive fitting, and a cultural acceptance of long timelines, you get a very different construction philosophy. One that can produce results that feel surprising to us precisely because we no longer work that way. None of this requires advanced lost technology. It requires a different relationship to material, labour and time. It requires patience elevated to a system. Before machines, before metal, before mistakes could be fixed cheaply, builders had to be careful. That care shows up in stone that still fits today. As we move onward, the focus will shift toward the kinds of knowledge that support such care. Because once you accept that ancient builders were not rushing, not improvising wildly, and not relying on brute force, a different picture begins to form. One where stone was shaped not by domination, but by a long conversation carried out over years, guided by experience rather than urgency. And from there, the next question naturally arises. If such knowledge existed, how was it preserved, shared, and eventually lost? There is a kind of knowledge that doesn't announce itself. It doesn't demand attention, doesn't scale easily, and doesn't survive well once the conditions that support it disappear. It lives in repetition, in habit, in the small decisions made correctly so often that they stop being noticed. This is the kind of knowledge that ancient stonework seems to reflect, and it is largely absent from the way we build and think today. When people speak about lost knowledge, they often imagine dramatic secrets, guarded formulas, or hidden machines. But most knowledge that disappears does so quietly. It fades, not because it was forbidden or destroyed, but because it was no longer needed. Once faster methods arrive, slower ones seem unnecessary. Once force becomes cheap, finesse feels inefficient. Over time, the skills that depend on patience and sensitivity simply stop being practiced. The stone structures that still stand from deep antiquity suggest a way of working that required constant attention to material behaviour, not occasional attention, not theoretical understanding, but daily embodied awareness. Builders would have known how stone sounded when it was healthy, how it sounded when it was stressed, how it felt under pressure, how it responded to moisture, heat, and time. This kind of awareness is not taught in manuals. It is learned through hands-on exposure, over years. In modern contexts, that exposure is rare. Machines insulate us from materials. We press buttons, and material yields. If it doesn't, we apply more power. There is little incentive to notice subtle resistance or early warning signs. The machine absorbs them. The human operator is separated from the process. Ancient builders did not have that separation. Every action required effort. Every change in the stone required intention. This forced attentiveness. When your hands are directly involved, you cannot ignore feedback. The material speaks constantly, and you must listen or risk failure. Listening, in this sense, is not metaphorical. Stone transmits information through vibration. A strike produces a sound that reflects internal structure. A crack begins with a change in tone before it becomes visible. Pressure feels different depending on grain orientation. Moisture changes friction. Temperature changes brittleness. These signals are subtle, but they are consistent. In crafts that still survive without heavy mechanization, similar sensitivities remain. A skilled woodworker knows when a piece of wood is about to split. A potter knows when clay has reached the right consistency without measuring moisture content. A blacksmith knows when metal is ready to move by colour and resistance. None of this is mystical, it is learned perception. Stoneworking at the level seen in ancient precision masonry would have required comparable perception. The difference is that stone is less forgiving. Errors are more costly. This increases the need for restraint. One aspect of quiet knowledge is knowing when not to act. Modern systems reward intervention. If something is not progressing, you apply force. Ancient systems often rewarded waiting, allowing moisture to penetrate, allowing temperature to stabilize, allowing stress to redistribute. Time itself was part of the process. We tend to treat time as something to be minimized. Ancient builders often treated time as a tool, soaking stone for days or weeks, allowing it to dry slowly, repeating cycles of wetting and drying to weaken surface bonds. None of this leaves dramatic evidence behind, but it changes how stone behaves. There is also evidence that ancient builders understood seasonal timing. Certain stones behave differently depending on temperature and humidity. Quarrying during one season and shaping during another may have reduced cracking. Construction may have paused not because of inconvenience, but because conditions were unfavourable. This kind of environmental awareness is largely absent from modern construction, which seeks to control conditions artificially. Climate-controlled environments allow work to proceed year-round, but they also remove incentives to adapt methods to natural rhythms. Another piece of quiet knowledge involves selection. Not all stone is equal, even within the same quarry. Ancient builders appear to have been selective in ways that go beyond visible quality. Stones may have been chosen based on sound, weight, or subtle surface features. This selection process would dramatically reduce later problems. Modern extraction prioritizes volume and uniformity. Blocks are cut according to size and shape requirements. Internal variation is often ignored until it causes failure. Ancient selection likely prioritized behavior over appearance. Then there is the knowledge of sequence. Not everything needs to be done at once. Certain actions prepare the material for later steps. Shaping one surface before another may reduce stress. Allowing a stone to rest between stages may prevent microfractures from propagating. Rest is not something we associate with construction today. But materials do respond to stress over time. Removing material changes internal stress distribution. Allowing that stress to settle before continuing can prevent unexpected failures. This is standard practice in some modern engineering contexts, but it is rarely discussed in relation to ancient work. Quiet knowledge also includes knowing the limits of force. There is a threshold beyond which additional effort produces diminishing returns or damage. Skilled workers learn where that threshold lies. They operate below it deliberately. In ancient stonework, this threshold awareness may explain why some surfaces appear gently shaped rather than aggressively cut. Material was removed only to the point necessary to achieve fit. Excess removal was avoided. This restraint has consequences. It produces stones that retain mass and strength. It preserves natural load-bearing capacity. It also results in surfaces that feel organic rather than geometric. Another dimension of this knowledge is communal memory. Techniques were not isolated discoveries. They were embedded in social structures. Apprentices learned from masters. Groups developed shared standards. Correction was immediate and collective. When such systems collapse, the knowledge does not transition easily. Written records cannot capture embodied skill. Even if instructions survive, the field does not. Without continuous practice, the knowledge becomes inert. This may help explain why later cultures sometimes struggled to replicate earlier stonework, even when they occupied the same sites. The stone remained, the environment remained, but the chain of practice was broken. There is also evidence that some ancient knowledge was intentionally conservative. Innovations were adopted slowly. Methods that worked were preserved. This conservatism is often framed negatively, but it has advantages. It prevents unnecessary experimentation on critical structures. It ensures reliability. Modern innovation culture rewards novelty. Ancient building culture likely rewarded stability. If a method had proven itself over generations, there was little incentive to replace it. Quiet knowledge is also often local. What works in one region may not work in another. Stone type, climate, and seismic activity all influence method. This leads to diverse solutions rather than universal ones. When we search for a single lost technique, we may be asking the wrong question. There may have been many techniques, each adapted to context, each refined through local experience. Another factor that makes this knowledge difficult to recover is that it does not scale well. Methods based on patience and sensitivity cannot be easily industrialized. They require skilled individuals, they require time, they resist standardization. As societies grow and construction demands increase, such methods become less practical economically. Faster methods replace them, even if the results are less durable. Over centuries, the slower methods fade from memory. This does not mean they were inferior. It means they were mismatched to changing priorities. Quiet knowledge also includes an ethical dimension. Ancient builders may have felt responsibility not just to patrons, but to future generations. Structures were meant to endure beyond the builder's lifetime. That changes how one approaches mistakes. If you know you will never see the structure completed, but others will live with the result, you may be more cautious. You may favour methods that minimise long-term risk over short-term convenience. Modern construction often operates under different incentives. Projects are bounded by contracts, budgets and deadlines. Long-term maintenance is someone else's problem. This encourages different decisions. When we look at ancient stonework through modern eyes, we often miss this shift in values. We assume inefficiency where there was intention. We assume mystery where there was discipline. None of this suggests that ancient builders had perfect knowledge. Mistakes still happened. Structures still failed. But the system as a whole favoured learning from failure rather than masking it. Another subtle form of quiet knowledge is the use of non-verbal cues. Gesture, rhythm and shared movement coordinate work without explicit instruction. Teams learn to move stones together smoothly. They develop timing. This reduces sudden stress and improves control. Force applied smoothly is less damaging than force applied abruptly. Ancient methods likely emphasize gradual application, pulling, levering and settling stones into place over time rather than dropping or forcing them. This approach aligns with what we see in stones that appear to have settled into their positions rather than slammed into them. Quiet knowledge also encompasses what we might call negative space, knowing what not to build, where not to place stones, when to stop expanding. Some ancient sites show signs of restraint, areas left unfinished or deliberately simple. This suggests an awareness of limits. Modern thinking often equates more with better. Ancient thinking may have been more selective. Recovering this kind of knowledge is difficult because it requires not just tools but mindset. It requires slowing down. It requires attention. It requires accepting that not all progress is measured in speed. When modern researchers attempt to replicate ancient stonework, they often focus on replicating results rather than process. They ask how to achieve the same precision using modern tools. That approach misses the point. The ancient process may have depended on constraints that modern tools remove. To truly understand, one would need to adopt similar constraints, work slowly, use simple tools, accept failure, learn to read material feedback. That kind of experiment is rarely funded or prioritized, and yet some individuals do attempt it. Craftspeople, experimental archaeologists and traditional builders quietly rediscover aspects of these methods. Their results are often dismissed as anecdotal, but they point toward a body of knowledge that still exists at the margins. This knowledge is quiet because it does not advertise itself. It does not produce dramatic breakthroughs. It produces steady, reliable results over long periods. In a culture that values speed and novelty, that kind of knowledge is easy to overlook. As this exploration continues, attention will turn towards specific mechanisms that may have supported this quiet knowledge, not as isolated tricks but as parts of a larger system. Vibration, moisture, gravity, sequence. Each plays a role. For now, it is enough to recognize that what appears lost may simply be unused. Not forgotten entirely, but no longer practiced widely. And knowledge that is not practiced does not remain alive. Stone remembers what hands once knew. It holds the shape of decisions made carefully, slowly, and repeatedly. And while we may not yet understand every step that led to those shapes, we can begin by acknowledging that the knowledge behind them was not loud or dramatic. It was quiet, disciplined, and deeply attentive. From there, the next question naturally follows. If such quiet knowledge existed, what physical principles did it rely on? And how might something as simple as sound or vibration have played a role without ever being recognized as technology in the modern sense? Stone is often treated as the opposite of sound. One is solid, unmoving, silent. The other is fleeting, invisible, gone as soon as it arrives. But in reality, stone is never silent. It carries sound remarkably well. It transmits vibration efficiently. It responds subtly but consistently to rhythmic energy. And once you start paying attention to that relationship, a different way of thinking about ancient stonework begins to emerge. Every solid object has natural frequencies at which it prefers to vibrate. Strike it, rub it, or apply repeated pressure, and it responds. Sometimes that response is audible. Sometimes it is felt through the hands. Sometimes it appears only as a change in resistance. Stone is no exception. In fact, dense stone like granite or basalt can transmit vibration over long distances with very little loss. Modern engineering relies on this fact constantly. Vibrational analysis is used to detect cracks in bridges, stress in buildings, flaws in aircraft components. A structure does not need to break to announce that something is wrong. It changes how it vibrates first. Long before visible damage appears, sound carries the warning. Ancient builders did not have oscilloscopes or sensors, but they did have ears, hands, and time. In a quiet working environment, small differences in sound become noticeable. A stone struck at one point rings differently than when struck at another. A block with internal fractures sounds dull compared to one that's intact. Even the way two stones sound when tapped together can reveal how well they fit. This is not speculation. It is a practice still used today by stonemasons, sculptors, and quarry workers in parts of the world. They tap stone and listen, not symbolically, literally. Sound tells them where to strike, where not to, and when to stop. When you begin to view ancient stonework through this lens, certain patterns take on new meaning. Consider stones that show little evidence of aggressive cutting but appear finely shaped. Instead of repeated hard impacts, imagine sustained rhythmic tapping. Light strikes, repeated thousands of times, each one delivering minimal force but reinforcing a consistent vibrational pattern. Over time, vibration can do surprising things. It can reduce friction. It can encourage micro-fractures to propagate in predictable directions. It can allow grains within a stone to shift slightly, relative to one another. None of this happens quickly, but ancient construction was not quick. One of the most interesting aspects of vibration is resonance. When energy is applied at a frequency that matches an object's natural frequency, the effect is amplified. A small input produces a large response. This is why a glass can shatter from a singer's voice under the right conditions. It's also why bridges can fail catastrophically if wind induces resonant oscillations. Stone too has resonant frequencies. These frequencies depend on size, shape, density, and internal structure. A builder who repeatedly worked with similar stones would begin to recognize these responses intuitively. Certain rhythms would feel right, others would feel ineffective or dangerous. This doesn't require formal knowledge of physics, it requires experience. Over years, patterns emerge. Stones respond better when worked in certain ways. Less force is needed, cracks behave more predictably, surfaces become easier to refine. This kind of knowledge would be especially valuable when working without hard cutting tools. Instead of overpowering the material, builders could encourage it to behave in desired ways. Sound becomes a guide, not a byproduct. There are ancient accounts, scattered across cultures, that mention stone responding to sound. In some cases, these are wrapped in myth or ritual language. Stones that move when sung to. Stones that soften at certain times. Stones that listen. Modern interpretations often dismiss these as symbolic or fantastical. But symbolism does not exclude practical observation. In societies without formal scientific language, metaphor is often used to describe real effects. Saying that stone listens may simply mean that it responds. Even today, we use similar language. We say a machine sounds wrong. We say wood feels dead. We say a structure hums. None of these statements are poetic in intent. They are practical shorthand for sensory information. Imagine a construction site where sound mattered, where workers paid attention to the tone produced when stone was struck or rubbed, where changes in sound signalled when to continue or stop. Over time, this attention would shape technique. Sound is not the only form of vibration involved. Rhythmic motion, such as rocking, rolling, or swaying heavy stones, also induces vibration. Repeated movement can reduce static friction and make large objects easier to move. This is well understood in modern physics and logistics. There are documented cases where large stones can be moved with surprisingly little effort once they are set into rhythmic motion. The initial force is high, but once movement begins, maintaining it requires far less energy. The key is consistency rather than strength. Ancient transport methods likely relied heavily on this principle. Stones may not have been dragged continuously. They may have been rocked, nudged, and settled incrementally. Each movement small but cumulative. This same principle applies at smaller scales. When shaping stone, maintaining a steady rhythm allows material to respond gradually. Abrupt force causes unpredictable fracture. Gentle repetition encourages controlled change. There is also evidence that vibration combined with moisture can significantly alter stone behaviour. Wet stone transmits vibration differently than dry stone. Water reduces friction and can act as a medium that distributes energy more evenly across surfaces. Repeated wetting and vibrating of stone can weaken surface bonds without damaging internal structure. This would make fine shaping easier while preserving overall strength. Again, this does not require advanced technology. It requires patience and observation. Some modern experiments support this idea. Ultrasonic tools use high-frequency vibration to cut or shape hard materials with minimal force. While ancient builders did not have ultrasonic generators, they did have the ability to generate rhythmic sound and motion over long periods. Lower frequency vibration, applied consistently, can still have an effect. It may take longer, but ancient construction timelines allowed for that. One of the reasons this line of thinking is often dismissed is because modern demonstrations focus on dramatic effects. We look for stones levitating or melting. When that doesn't happen, we conclude sound is irrelevant. But ancient methods may have been far subtler. A reduction in required force by even a small percentage would be significant over time. A method that reduces cracking risk slightly would be adopted. A technique that makes fitting easier, even marginally, would be valuable. Quiet improvements accumulate. Over generations, they become standard practice. Another factor to consider is communal rhythm. Large groups working together naturally fall into synchronized movement. Chanting, counting, or calling out time helps coordinate effort. This produces consistent force application and reduces sudden stress. Such coordination is often framed as ritual in historical accounts, but it also serves practical purposes. It synchronizes pulling. It regulates breathing. It maintains steady application of force. Stone responds better to steady force than to erratic force. Coordinated rhythm improves outcomes even if participants do not consciously understand why. Listening stone in this context does not mean stone with awareness. It means stone as a responsive medium. Builders listen not because stone hears, but because listening reveals how stone responds. This listening would extend beyond sound. Vibration can be felt through the body. Subtle changes in resistance communicate information. A stone that resists evenly is healthy. A stone that suddenly stiffens or softens indicates a change. Hands become instruments. Feet feel ground response. Tools transmit feedback. Over time, workers learn to interpret these signals without conscious thought. Modern mechanization suppresses this feedback. Power tools isolate operators from vibration. Protective equipment reduces sensation. Efficiency increases, but sensitivity decreases. This may be why modern attempts to replicate ancient stonework often struggle. The tools used overwhelm the feedback that guided ancient methods. Researchers apply too much force too quickly, then conclude that ancient precision was impossible without advanced tools. But the ancient approach may have been the opposite: less force, more feedback; less speed, more control. Sound also plays a role in quality control. Finished stones can be tested acoustically. Tap a stone and listen. A clear ring suggests integrity. A dull thud suggests internal flaws. Stones that sound wrong can be rejected before placement. This would dramatically reduce structural failure. It also explains why some stones appear overbuilt. Only the best stones would be selected for critical positions. There is also the possibility that certain sound frequencies were used intentionally to assist shaping, not in a mystical sense, but in a practical one. Repeated tapping at a frequency that encourages fracture along desired planes could make splitting stone more predictable. Quarry workers today sometimes use controlled percussion, rather than single heavy blows. This produces cleaner breaks. Ancient quarrying techniques likely relied on similar principles. Vibration may also help explain how stones were fitted so closely without visible gaps. When two stones are rubbed together with fine, abrasive undervibration, high points wear down first. This produces complementary surfaces that match increasingly well. This is a self-correcting process. The better the fit, the more evenly pressure is distributed, and the slower material is removed. Eventually the surfaces reach equilibrium. This method does not require measuring, it requires patience. It also produces fits that are difficult to achieve by cutting alone. The absence of visible tool marks on some stones may be a result of such finishing processes. Abrasion and vibration leave different signatures than cutting. Over time, these signatures can be subtle. Sound-based methods also leave little archaeological trace. No specialized tools remain. No distinctive marks are obvious. The evidence is in the fit itself, which is why it is often overlooked. Listening stone also connects to a broader worldview. In many ancient cultures, materials were not considered inert. They were seen as active participants in the world. This does not mean people believed stone was alive in a modern biological sense. It means they recognized responsiveness. Such a worldview encourages attentiveness. If material is responsive, you pay attention. If it is dead and passive, you force it. That difference in attitude shapes technique. It is also worth noting that sound-based practices do not require literacy. They are easily transmitted orally and physically. A master can demonstrate a rhythm. An apprentice can mimic it. Feedback is immediate. This makes such knowledge robust within a culture but fragile across disruption. When the chain breaks, the knowledge vanishes almost without trace. Modern science often struggles to take such knowledge seriously because it resists quantification. It does not produce formulas, it produces outcomes. Without documentation, it is easy to dismiss. But absence of documentation is not evidence of absence, especially in cultures where writing was rare or reserved for other purposes. Ancient builders did not isolate variables in controlled experiments, but they did observe outcomes repeatedly. Over generations, patterns become reliable knowledge. Listening stone is not about secret techniques, it is about sensitivity, about recognizing that material behavior carries information and that paying attention to that information improves results. Once you accept that possibility, many features of ancient stonework become less mysterious. Not simple, but less alien. The stones fit because they were guided into fitting. The precision emerges not from overpowering material, but from responding to it. Water does not look like a tool. Gravity does not feel like a technique. Weight does not announce itself as a method, and yet these three forces have shaped more stone on Earth than any blade or hammer ever has. They work slowly, they do not rush, they do not correct mistakes, they simply apply themselves continuously, patiently, and without exception. Ancient builders lived inside these forces, not outside them, and much of their quiet knowledge may have come from understanding how to let these forces do the work instead of fighting them. Modern construction often treats gravity as a problem to be overcome. We calculate loads, design reinforcements, and actively resist weight with steel and concrete. Water, likewise, is something to exclude, divert, or seal out. Moisture is an enemy, weight is stress, gravity is a constraint. Ancient construction appears in many cases to have taken a different approach. Rather than resisting these forces, it worked with them. Rather than trying to defeat gravity, it allowed gravity to finish the work. Rather than keeping stone perfectly dry, it used water as part of the process. This shift in perspective changes what is possible. Let's begin with water, because its effects on stone are subtle but profound. Stone may appear impermeable, but most stone is porous at microscopic scales. Water seeps into cracks too small to see. It travels along grain boundaries. It alters friction. It carries dissolved minerals. It expands when it freezes. It contracts when it evaporates. Over time, these actions change how stone behaves. Ancient builders would have observed this even without formal theory. A stone freshly quarried behaves differently from one that has dried. Wet stone can be easier to work in certain ways. It transmits vibration differently. Abrasives behave differently on wet surfaces. Heat dissipates more evenly. Repeated wetting and drying cycles can weaken surface bonds without compromising internal strength. This is particularly useful when the goal is fine surface shaping rather than bulk removal. Instead of striking harder, builders could wait. Allow water to do part of the work invisibly. There's also evidence that water was used intentionally during transport. Wetting sled paths reduces friction dramatically. Adding moisture to sand or clay changes how it compacts under load. Water turns loose particles into cohesive surfaces. This is basic physics, but it is powerful when applied consistently. Some ancient depictions and accounts show stones being moved with water involved, though these are often dismissed as symbolic. But symbolism often reflects practice. Pouring water in front of sleds, wetting the ground, or using mud to stabilize movement would all make sense. Weight itself then becomes an ally. A heavy stone pressing down on a lubricated surface behaves predictably. It settles. It resists sudden motion but responds well to gradual force. This makes controlled movement possible without needing enormous bursts of energy. Now consider shaping and fitting. When two stones are placed together under weight, gravity ensures continuous contact. High points experience more pressure, low points experience less. If abrasive material is present between them, even very fine abrasive, the pressure naturally focuses material removal where it is needed most. This is an extraordinarily elegant process. It requires no measuring, no marking, no planning beyond placing stones together and allowing gravity to act. Over time, surfaces conform to one another. The fit improves automatically. This method is slow, but ancient builders were not in a hurry. It also explains why some fitted stones appear to have complementary curves. Gravity encourages equilibrium. Surfaces settle into shapes that distribute load evenly. Sharp edges wear down. Broad contact areas develop naturally. This is not guesswork. It is how lapping works in modern engineering. Precision surfaces are often produced by rubbing components together with fine abrasives under controlled pressure. The process produces flatness and fit beyond what cutting alone can achieve. The difference is that modern lapping uses machines to speed things up. Ancient builders could achieve similar results by using weight and time. Gravity also plays a role in error prevention. When stones are shaped under their own weight rather than by external force, the risk of catastrophic fracture is reduced. Stress is distributed gradually. There are no sudden shocks. The stone settles rather than resists. This aligns with the absence of violent fracture marks on many ancient stones. Instead of being chipped aggressively, surfaces appear worn, refined, eased into place. Water enhances this process further. It carries away debris. It prevents overheating during abrasion. It lubricates contact surfaces. It reduces dust, which can interfere with tactile feedback. Working stone wet is messier, slower, and less dramatic. It also produces cleaner results. There is also a thermal aspect. Temperature changes affect stone behaviour. Cold stone is more brittle. Warm stone is slightly more forgiving. Water moderates temperature fluctuations. It absorbs heat generated by friction. This stabilizes the working environment. Ancient builders may not have articulated this in scientific terms, but they would have observed the effects. Certain times of day or year would be better for certain tasks. Shaping might be done when stone was cool and wet. Transport might be done when ground conditions were favourable. This sensitivity to timing is part of the patience embedded in ancient methods. Rather than forcing work to continue under unfavourable conditions, builders could wait. Construction timelines allowed for that flexibility. Gravity also governs placement. When a stone is lowered slowly into position, gravity guides it. If surfaces are well prepared, the stone finds its place. It settles with a sense of inevitability. This is very different from forcing a stone into position with lateral blows. Some ancient stones appear to have been lowered into sockets or cradles rather than slid horizontally. Vertical placement allows gravity to do most of the work. Lateral movement under load is minimized. This also explains why some stones show little evidence of horizontal scarring. They may not have been dragged into place after final shaping. Instead, they were positioned carefully and allowed to settle. Weight also contributes to long-term stability. When stones are heavy enough, friction between them increases. The structure becomes self-locking. Mortar becomes unnecessary. In seismic regions, this approach has advantages. During an earthquake, stones can move slightly, dissipating energy. When the shaking stops, gravity pulls them back into alignment. The structure survives because it is allowed to move. Rigid structures resist movement until they fail. Flexible systems accommodate movement and endure. Ancient builders may not have used the word flexibility, but they understood the effect. Walls that survive repeated earthquakes teach lessons. Over generations, those lessons become standard practice. Water also plays a role long after construction is complete. Rain, humidity, and groundwater interact with stone continuously. Structures designed to work with moisture rather than against it age more gracefully. Some ancient stones show signs of mineral deposition at joints. Water carries minerals that crystallize as it evaporates. These deposits can actually tighten joints over time, acting as a natural cement without the brittleness of mortar. This process is slow and depends on environmental conditions, but over centuries it contributes to stability rather than degradation. Modern construction often tries to isolate materials from environmental interaction. Sealants, barriers, and coatings aim to freeze a structure in time. Ancient structures often allowed interaction and relied on balance rather than isolation. This approach requires patience not just during construction, but across generations. Builders had to trust that the structure would improve with time rather than degrade immediately. Weight and gravity also inform how stones were selected and oriented. Stones have grain. They have natural planes of weakness. Placing a stone so that gravity aligns with its strongest orientation increases durability. This kind of selection requires knowledge of stone behaviour under load. Builders would have learned which orientations failed and which survived. Over time, this knowledge would become intuitive. It is telling that many ancient stones are oriented consistently. Grain direction matters. This is something modern builders sometimes overlook because reinforcement compensates for mistakes. Without reinforcement, ancient builders had to get it right. The patience of gravity also extends to quarrying. Extracting stone without explosives requires time. Controlled cracking using wedges, water expansion, or thermal cycling allow stone to separate along natural planes. These methods are slow, but they preserve stone integrity. Explosives are fast, but they introduce microfractures that compromise long-term durability. Ancient quarry marks often show careful extraction, rather than violent removal. This results in stones that are stronger and more predictable during shaping and placement. Again, patience replaces force. One of the reasons modern observers struggle with this idea is that patience does not leave dramatic evidence. There are no spectacular tools to point to, no machines to reconstruct. The evidence is negative, the absence of certain kinds of damage. the presence of long-term stability. Water, weight, and gravity do not announce themselves as technologies. They are always present. That makes them easy to overlook. But ancient builders could not overlook them. Their entire working environment was shaped by these forces. Ignoring them would have led to failure. Instead, they learned to cooperate. This cooperation changes the role of the builder. Instead of being a conqueror of material, the builder becomes a facilitator, someone who sets conditions and allows natural forces to complete the task. This mindset aligns closely with what we see in fitted stonework. The builder prepares surfaces, positions stones, introduces water or abrasive, applies steady pressure, and waits. Waiting is not inactivity. It is part of the process. In modern contexts, waiting is often seen as waste. In ancient contexts, waiting may have been understood as work. There is also an economic dimension. Labour was abundant. Time was abundant. Energy was scarce. Using gravity and water efficiently conserved energy. It reduced injury. It reduced material loss. These are practical considerations, not philosophical ones. When modern reconstructions fail to replicate ancient results, it is often because they attempt to compress time. They try to achieve in days what ancient builders achieved in months or years. They apply more force to compensate. The results differ. If instead, time were allowed to stretch, if gravity were allowed to act without interference, outcomes might converge. This is difficult to test experimentally because it requires long-term commitment. It does not produce quick results. It does not fit well with modern research funding cycles. And yet, the stones themselves are long-term experiments that have already run. Their continued stability is data. Their fit is evidence. One of the most frustrating things about studying ancient stonework is that so much of what we are looking for may already be in front of us. Not buried, not erased, not deliberately concealed, simply overlooked. Techniques hidden in plain sight are often the hardest to recognize because they don't look like techniques at all. They look like the natural outcome of work done competently, repeatedly, and without spectacle. When modern observers approach ancient structures, they often search for evidence that matches modern expectations. Tool marks that resemble saw cuts, drill holes with familiar profiles, straight lines where machines would leave straight lines. When those markers are missing, the assumption is often that something mysterious must be involved, or that erosion has conveniently removed the evidence. But there is another possibility that is both simpler and more unsettling. The techniques used may not leave the kinds of marks we are trained to notice. Many ancient stone surfaces do not show aggressive cutting. Instead, they show wear, subtle smoothing, gradual transitions between planes, edges that are softened rather than sharply defined. To a modern eye, this can look unfinished or weathered, but in context it may be intentional. Consider how modern precision surfaces are sometimes produced. In engineering, when extreme flatness is required, components are not always cut to final shape, they are lapped. Two surfaces are rubbed together with fine abrasive under controlled pressure. The process is slow, material removal is minimal. The result is a surface that conforms perfectly to its counterpart. If you examine ancient stones that fit with remarkable precision, many of them show characteristics consistent with this kind of process. The surfaces are not perfectly planar in isolation. They are planar relative to one another. This distinction matters. A stone does not need to be geometrically flat in an absolute sense to fit perfectly. It needs to match its neighbour. This is an important shift in perspective. Instead of imagining ancient builders striving for abstract perfection, it is more plausible that they were striving for relational perfection. Fit mattered more than form. Relational methods are easy to miss because they do not produce standardized shapes. Each stone becomes unique. There is no template to compare against. Without seeing the process, the result looks anomalous. Another technique that hides in plain sight is sequencing. Modern analysis often treats stones as isolated objects. We measure one block, then another, and compare them individually. Ancient builders would have thought in sequences. Which stone goes first? Which surface defines the next? Which adjustment affects the entire structure? Evidence of this can be seen in stones that appear oddly shaped until viewed in context. Remove one stone, and the surrounding stones suddenly look incomplete. Their shapes make sense only in relation to what is missing. This implies a process where stones were shaped to each other progressively, not independently. This progressive shaping leaves no obvious signature beyond the final fit. There are no guide marks, no reference lines left behind. Once the stones are in place, the process disappears. Another overlooked technique involves restraint in removal. Many ancient stones retain large amounts of their original mass. Instead of being carved down to simple shapes, they are modified only where necessary. This reduces waste and preserves strength. Modern cutting techniques often remove more material than necessary because it is easier to do so. Ancient methods likely favoured minimal intervention because material removal was costly in terms of time and risk. This minimalism shows up in stones with irregular outlines but precise contact surfaces. The exterior may look rough or unfinished, while the hidden faces fit perfectly. This tells us where the effort was concentrated. Hidden effort is another theme. Much of the most careful shaping occurs on surfaces that were never meant to be seen. Faces that would be buried inside walls or pressed against other stones are often the most precisely finished. Visible faces may be comparatively rough. This reverses modern priorities. Today, finishes are often applied for appearance. Structural surfaces are hidden and sometimes less refined. Ancient builders appear to have prioritized function over display. If you approach ancient walls expecting decorative perfection, you may miss structural sophistication. There is also the issue of scale. Some techniques operate differently at different scales. What looks crude up close may function perfectly at the scale of the structure. Slight curvature that is invisible to the eye can have significant structural effects. Many ancient stones exhibit subtle curvature, faces that are not perfectly flat but slightly convex or concave. This curvature is often too consistent to be accidental. It improves load distribution and contact. Detecting this requires careful measurement. Casual observation often misses it. Without measuring tools or an expectation that curvature might be intentional, it is easy to dismiss. Another technique hidden in plain sight is the use of natural stone geometry. Stones are not cut randomly. They are oriented. Grain direction, bedding planes, and natural fracture lines influence how stones are shaped and placed. Ancient builders likely selected stones based on how they would behave under load. A stone that fractures easily along one plane may be ideal if oriented correctly. A stone that resists fracture may be reserved for critical positions. Once placed, this selection becomes invisible. The stone simply sits there. Unless you know what to look for, the decision-making process is lost. There is also the question of incremental adjustment. Modern cutting often aims for final dimensions quickly. Ancient shaping may have involved many small adjustments spread over long periods. This incremental approach produces surfaces that lack obvious tool marks. Each adjustment is tiny. Over time, the surface evolves smoothly. The process leaves no dramatic evidence. This is similar to erosion but controlled. Instead of random wear, there is directed wear guided by fit and contact. Because erosion is familiar, we may misinterpret controlled wear as natural weathering. But the context matters. When such surfaces are found in protected locations, shielded from environmental exposure, erosion becomes an unlikely explanation. Another hidden technique involves temporary materials. Organic tools, wooden forms, fibre bindings, plant-based abrasives. These materials degrade quickly. They leave little trace. Modern archaeology tends to focus on durable artifacts. Stone tools survive. Metal tools survive. Organic tools rarely do. If critical techniques relied on organic materials, they would be underrepresented in the archaeological record. This creates a skewed picture. We reconstruct methods based on what survives. not necessarily on what was used most. For example, wooden mallets produce different effects than stone hammers. They deliver force differently. They reduce shock. They encourage controlled deformation rather than fracture. Such tools would be ideal for fine stone shaping, but they would leave little trace. Similarly, plant fibres soaked in abrasive slurry could be used for polishing or shaping. Once degraded, they leave nothing behind. Another technique that hides in plain sight is the use of gravity as a measuring tool. When two stones are placed together under their own weight, gravity ensures consistent contact. High points reveal themselves, low points remain untouched. This is self-correcting. No measurement is required. The stone tells you where to remove material. This method leaves no markings beyond the final fit. It does not require marking tools, measuring sticks, or reference lines. Everything happens through contact. Because modern construction relies heavily on explicit measurement, we often assume ancient builders must have done the same, but measurement is only one way to achieve precision. Feedback-based methods can be equally effective. There is also evidence that ancient builders used test stones, stones that were not part of the final structure but served as practice or reference. These may have been reused, reshaped, or discarded. Unless they are recognized as such, they may not stand out archaeologically. Learning leaves debris, but debris does not always look important. Another hidden technique involves rhythm and pacing. Work done rhythmically produces consistent results. Force applied at regular intervals behaves differently than force applied sporadically. This is true in many crafts. In stonework, rhythm helps maintain control. It also reduces fatigue and error. Rhythm leaves no trace. Once the work is complete, the cadence disappears. The same is true for teamwork. Coordinated effort allows precise movement of heavy objects. Communication may involve gestures, sounds, or simple cues. None of this survives. Modern reconstructions often underestimate the effectiveness of coordinated human labour. They imagine chaos where there may have been practiced efficiency. Another factor that hides techniques is that ancient builders may not have distinguished between construction and finishing the way we do. Shaping, fitting, and placing may have been continuous rather than separate stages. This blurs the evidence. There is no clear line where shaping ends and placement begins. Everything happens together. Modern analysis often tries to isolate stages. When that isolation fails, confusion follows. There is also the issue of modern bias toward complexity. We expect impressive results to require impressive tools. When we see impressive results without impressive tools, we assume something is missing. But complexity does not always require complexity. It can arise from simple processes applied consistently. Water dripping over stone creates caves. Gravity shaping sediment creates layers. Time amplifies small effects. Ancient builders worked with these forces rather than against them. Another hidden technique involves maintenance during construction. Stones may have been adjusted repeatedly as the structure grew. Load changes as stones are added. Surfaces may need refinement after placement. This ongoing adjustment would not leave clear evidence once complete. The structure would simply look finished. Modern construction often locks elements in place quickly. Ancient construction may have allowed structures to evolve gradually. There is also the role of intuition. Skilled workers make decisions that are difficult to articulate. They feel when something is right. That feeling is based on experience, not calculation. Intuition leaves no record. It cannot be excavated. This makes ancient methods difficult to reconstruct because we are looking for explicit instructions where none existed. Another reason techniques remain hidden is that we often assume ancient people worked in isolation from nature. In reality, they were immersed in it. They observed erosion, landslides, riverbeds, and rock faces constantly. Nature was their laboratory. They saw how stone broke, how it weathered, how it settled. Construction methods likely mimicked natural processes, but in controlled ways. When a wall resembles a natural rock formation in its stability, that may not be coincidence. We also tend to separate disciplines. Physics here, craft there, ritual somewhere else. Ancient cultures did not draw such hard lines. Work songs may have coordinated labour. Ritual timing may have aligned with environmental conditions. Practical and symbolic actions overlapped. This does not mean the work was mystical. It means it was integrated. Integration hides technique because it does not present itself as a discrete method. It is woven into daily life. When techniques are woven into life, they are hard to isolate and describe later. Another layer of invisibility comes from restoration. Many ancient sites have been restored using modern methods, mortar added. Stones replaced, surfaces cleaned. This can obscure original techniques. Modern intervention often overwrites ancient subtlety. In some cases, stones that once fit perfectly have been disturbed, then reset incorrectly. Gaps appear where none existed. This leads to misinterpretation of original workmanship. Hidden techniques also suffer from lack of incentive to search for them. Modern engineering has little need to rediscover slow methods when faster ones exist. Research tends to focus on novelty, not patience. As a result, ancient techniques that do not scale industrially receive less attention, yet the stones remain. They continue to demonstrate outcomes that challenge assumptions. The key to recognizing techniques hidden in plain sight is changing what we look for. Instead of asking what tool made this mark, ask what process produced this relationship. Instead of looking for evidence of force, look for evidence of restraint. Instead of searching for missing technology, consider missing priorities. Once that shift occurs, many features that seemed mysterious begin to feel consistent. Not easy, but coherent. This does not mean every question is answered. Some details remain elusive, but the overall picture becomes less about secrets and more about systems. Systems that relied on time, attention, and feedback. Systems that worked because they were practiced continuously, not because they were recorded. For now, it is enough to acknowledge that much of what we seek may already be visible, not hidden behind walls or buried underground, but present in the way stones meet, rest, and support one another. The challenge is not uncovering new evidence, but learning to see what has been there all along. There is an assumption woven deeply into modern thinking that important knowledge gets written down. If something matters, we expect it to appear in texts, diagrams, manuals, or records. When we don't find those records, we tend to conclude that the knowledge either never existed or was deliberately hidden. But for most of human history, writing was not the primary way knowledge lived. And for certain kinds of knowledge, writing was not just unnecessary, it was ineffective. The methods behind ancient stonework belong squarely in that category. Writing is good at preserving abstract ideas, laws, myths, transactions, lineages, prayers. It is far less effective at preserving embodied skill. You can describe how to balance on a bicycle, but the description will not teach someone to ride. You can explain how to shape stone, but without years of tactile experience, the explanation is mostly useless. Ancient builders understood this instinctively, even if they never articulated it as a theory. Stoneworking knowledge lived in the body, in the hands that learned how much pressure was too much, in the ears that recognized when a tone changed, in the posture that allowed weight to be applied smoothly, in the timing that prevented cracks. None of this translates well into words. Because of that, there was little reason to write it down. Most ancient writing systems emerged to serve administration, ritual, or power. They tracked harvests, taxes, offerings, royal decrees, and cosmological narratives. They were tools of organization and authority. Skilled labor, by contrast, was transmitted through apprenticeship. A master did not need a text to teach an apprentice. The apprentice watched, copied, failed, and corrected. Knowledge passed hand to hand. In many cultures, writing itself was restricted. Literacy was limited to specific classes. Builders were often not among them. Even if a master mason had wanted to record techniques, they may not have had access to writing, or writing may not have been considered an appropriate medium for that kind of knowledge. There is also the question of permanence. Writing freezes knowledge at a moment in time, but practical techniques evolve continuously. A method that works well in one quarry may need adjustment in another. A stone that behaves one way in dry weather may behave differently in humidity. Writing down a method risks turning it into a rigid prescription rather than a flexible practice. Ancient builders may have preferred adaptability over codification. Another important factor is that many of these methods would have seemed obvious to those practicing them. You do not write down instructions for breathing. You do not document how to walk. When a skill is universal within a community, it does not feel like knowledge that needs preservation. It feels like common sense. Only later, when the context changes and the practice disappears, does the absence become noticeable. This is one reason why ancient texts rarely describe everyday techniques in detail. They assume shared understanding. What gets written down is what needs explanation. What everyone already knows is left unwritten. Stoneworking methods, especially those practiced over generations, would have fallen into the category of assumed knowledge. There is also the issue of secrecy, though not in the dramatic sense often imagined. Skilled knowledge confers status. A master builder holds social and economic power. Their expertise is valuable. Sharing it widely could dilute that value, but secrecy does not require conspiracy. It can be as simple as limiting training to apprentices. Knowledge stays within families or guilds. It is protected by practice, not by prohibition. Writing it down would undermine that system. A written manual allows anyone with access to learn. Oral and embodied transmission maintains control. Guild systems in later periods operated on similar principles. Techniques were guarded, not because they were mystical, but because they were economically valuable. And even then, much of the knowledge was never written. It was demonstrated. Another reason these methods were not written down is that they did not present themselves as methods in the modern sense. There may not have been a clear boundary between technique and environment. Builders responded to conditions as they arose. They did not follow fixed recipes. Writing works best when processes are standardized. Ancient stonework often was not. If a method depends on listening to stone, adjusting pressure, waiting for moisture to act, responding to subtle changes, how do you write that down? You could try, but the text would be vague. It would rely on terms like enough, carefully, or until it feels right. Those words are useless without context. Because of this, many practical traditions rely on demonstration rather than description. Music is taught by listening and playing, martial arts by movement, craft by repetition. Stoneworking at this level belongs with those traditions. There is also a cultural dimension to consider. Many ancient societies did not conceptualize knowledge as something to be abstracted and archived. Knowledge was something you did, not something you possessed. It existed only in action. Once the action stopped, the knowledge ceased to exist in a meaningful way. From that perspective, writing it down would not preserve it. It would only preserve a shadow. Another factor is that much of ancient stonework knowledge was contextual rather than universal. What worked in one place did not necessarily work elsewhere. Stone type, climate, available materials, and social organization all mattered. A written manual would either have to be extremely long and complex or dangerously oversimplified. Neither would be useful. Instead, knowledge stayed local, passed within communities that work the same materials under the same conditions. This localization also explains why similar results appear in distant regions without direct contact. Different cultures arrived at similar solutions because they faced similar constraints and observed similar behaviors. Not because they shared written knowledge, but because they shared environments. There is also the issue of scale. Large construction projects often spanned decades or longer. Builders might spend their entire working lives on a single site. Knowledge accumulated slowly and was applied gradually. In such contexts, writing is less useful. There is no need to remind someone how to do something they do every day for years. The process itself is the memory. Writing becomes more important when tasks are intermittent or when people change frequently. Ancient building projects often involve stable communities and long-term continuity. That continuity breaks, and suddenly the knowledge is gone. We also need to consider the possibility that some writing did exist and simply did not survive. Stone inscriptions survive well. Papyrus, wood, bark and cloth do not. If technical notes were kept on perishable materials, they would be lost to time. But even if some documentation existed, it would likely have been minimal. Notes, reminders, diagrams meant for those already trained, not comprehensive manuals, and without the embodied context, such fragments would be nearly impossible to interpret. Another reason these methods were not written down is that ancient cultures often separated sacred and practical knowledge differently than we do. Building temples, tombs, or monuments was often a ritual act as well as a practical one. Instructions may have been embedded in ritual language, timing dictated by calendars, actions coordinated through ceremony. From a modern perspective, this looks symbolic or religious, but it may have encoded practical constraints. For example, building at certain times of year may align with optimal environmental conditions. Chanting may coordinate labour rhythm. Offerings may mark transitions between stages. None of this would be described as technique in a modern technical manual. It would appear in myth, liturgy, or tradition. When later observers strip away the ritual context, the practical knowledge disappears with it. There is also a philosophical shift to consider. Modern science values explicit explanation. Ancient craft valued reliable outcome. If something worked, it was sufficient. The urge to explain why something works, independent of doing it, is relatively recent. For most of history, explanation was secondary to practice. This means that ancient builders may not have conceptualized their methods in a way that lends itself to writing. They did not think in terms of principles. They thought in terms of actions. Actions do not translate cleanly into text. Another important point is that writing fixes authority. Once something is written, it can be referenced, challenged, or misused. Oral traditions are more flexible. They adapt. They change slightly with each generation, responding to new conditions. This flexibility is valuable when dealing with natural materials. Stone is variable. Methods must adapt. Writing down a technique risks turning it into dogma. Oral transmission allows correction. There is also the question of audience. Who would the writing be for? Apprentices did not need it. Masters did not need it. Outsiders were not intended to use it. Without a clear audience, writing has little purpose. In contrast, administrative records have clear audiences. Rulers, officials, traders. That is why they survive. Another layer to this is that some ancient societies actively distrusted writing for certain kinds of knowledge. Writing fixes things that may need to remain fluid. It removes knowledge from the social context that gives it meaning. In some traditions, knowledge only exists when practiced ethically and responsibly. Writing it down allows it to be detached from those safeguards. Whether or not this applied to stoneworking specifically, the general attitude toward knowledge matters. It is also worth noting that even in societies with extensive writing, practical crafts are often underdocumented. Medieval texts describe theology in great detail, but offer very little about how cathedrals were actually built. Renaissance treatises discuss proportions and ideals, but rarely the day-to-day techniques. We see the results and assume the methods must have been recorded somewhere. Often, they were not. This pattern suggests that the absence of written stoneworking manuals in antiquity is not unusual. It is expected. What makes ancient stonework feel exceptional is not the absence of writing, but the persistence of the results. These stones have outlived the knowledge that shaped them. This creates a mismatch. We have outcomes without instructions. We are accustomed to the opposite. When modern researchers encounter this, they often assume something must be missing. A lost text, a secret scroll, a vanished blueprint. But it may be that nothing is missing except the practice itself. Knowledge that lives in the body dies with the body unless it is continuously renewed. Writing cannot save it. This realization is uncomfortable because it implies that no archive, no excavation, no translation will fully recover these methods. At best, we can approximate them through experimentation and observation, and that requires adopting ancient constraints, working slowly, accepting failure, paying attention. It also requires humility, accepting that some forms of knowledge do not survive well in modern frameworks. The irony is that the more subtle and effective a technique is, the less likely it is to be documented. Dramatic innovations get recorded, quiet refinements do not. Stonework refined over centuries would not have felt revolutionary. It would have felt normal. Normal things rarely get written down. As this exploration moves forward, this absence of writing becomes less of a mystery and more of a clue. It tells us what kind of knowledge we're dealing with. Not theoretical, not abstract, not easily transferable. It was lived. And that leads naturally to the next question. If these methods were not written, and if they were practiced locally and embodied, how did similar approaches appear across distant regions? Why do we see echoes of the same quiet logic in stonework separated by oceans? When similar solutions appear in distant places, the first instinct is often to look for contact. Trade routes, migrations, lost maps, shared teachers. It is comforting to imagine knowledge moving cleanly from one culture to another, carried by travellers or preserved by a forgotten civilization. But stone tells a different, quieter story, one that does not require a single origin or a grand transmission, one that emerges naturally wherever humans spend enough time working carefully with the same stubborn material. Across continents separated by oceans and millennia, certain features repeat. Not styles, not symbols, not decorative motifs, methods, priorities, decisions embedded in stone that suggest a shared way of thinking rather than shared instructions. Walls built without mortar that flex instead of cracking. Stones shaped to fit neighbours rather than templates. Subtle curves where straight lines would have been easier. Load distributed through geometry instead of reinforcement. These similarities are not perfect copies. They are variations on a theme. Each region adapts to its own stone types, climate, terrain, and cultural needs. And yet, the underlying logic feels familiar, as though different groups arrived at the same conclusions by listening to the same material long enough. In the Andes, massive stones interlock with astonishing precision. Their outlines are irregular, but their joints are exact. In Egypt, granite blocks show surfaces that are flat and true, cut with care that exceeds what seems necessary for visual effect. In parts of Japan, stone walls use angled placements and carefully balanced weight to withstand earthquakes. In the Mediterranean, ancient retaining walls use dry stone techniques that rely entirely on gravity and fit. These places did not share languages, they did not share writing systems, they did not share religions. What they did share was stone, gravity, water, and time. When humans work with the same material under similar constraints, similar solutions tend to emerge. This is not coincidence, it is convergence. Consider agriculture. Farming practices arose independently in multiple regions because humans everywhere face the same challenge of feeding themselves. Different crops, different climates, similar principles. Stoneworking follows a similar pattern. Wherever people needed durable structures and lacked industrial tools, they learned to work with stone patiently and precisely. This does not mean the knowledge was identical everywhere. It means the material rewarded certain behaviours consistently. Stone favours compression over tension. It favours gradual force over sudden impact. It favours broad contact over point loading. Anyone who works with stone long enough will learn these lessons. Over generations, those lessons harden into tradition. One of the strongest indicators of shared logic rather than shared contact is the way mistakes are avoided. In many distant regions, builders independently arrived at techniques that reduce cracking risk. Rounded internal corners, interlocking joints, minimal reliance on mortar. These choices are not stylistic, they are structural. If one culture had taught another, we might expect to see the same mistakes repeated along with the successes. Instead, we see local adaptation, different joint patterns, different stone sizes, different construction sequences. The commonality lies in outcomes, not methods. This suggests that the knowledge was not transmitted as instruction, but rediscovered repeatedly. Another clue lies in what is absent. There is no universal ancient stoneworking manual, no standardized system that appears everywhere. Instead, there are families of solutions, each tuned to context. In Peru, stones often have multiple faces that meet different neighbours, creating complex three-dimensional fits. In Egypt, large blocks emphasize flatness and alignment over interlocking shapes. In Japan, angled stacking and careful drainage are prioritized. Each approach solves local problems effectively. The echo is not in the shape of the stones, but in the attitude toward them. That attitude values patience, it values feedback, it values cooperation with material rather than domination. This is not a mystical worldview, it is a practical one. When tools are limited, material behavior becomes the teacher. Another important factor is seismic activity. Regions prone to earthquakes often develop construction methods that allow movement. Dry stone walls appear again and again in such regions, not because people copied each other, but because walls that survive teach lessons. If a rigid wall collapses, it is rebuilt differently next time. If a flexible wall survives, that method persists. Stone remembers earthquakes. Builders learn from stone. Climate also shapes technique. In wet environments, drainage matters. Stones are angled, gaps are intentional, water is guided rather than trapped. In dry environments, massive blocks retain thermal stability. Walls are thick, joints are tight. These adaptations are local, but the underlying principle is the same. Work with the environment, not against it. There is also the role of labour organisation. Large stone projects require coordination. Coordination favours rhythm. Rhythm favours steady force. Steady force favours controlled outcomes. These dynamics appear wherever large groups move heavy objects together. Chanting, counting, synchronized movement. These are human responses to shared physical effort. They arise naturally. They are not taught from one culture to another. They are rediscovered. When such coordination becomes habitual, it influences technique. Stones are moved smoothly, placed gently, adjusted gradually. Again, the echo is behavioural, not instructional. Another point worth considering is that ancient people were not isolated from one another in time, even if they were in space. Humans everywhere share similar bodies, similar sensory capacities, similar cognitive patterns. We learn through trial, error, and imitation. When faced with similar problems, similar brains often produce similar solutions. This is especially true for problems constrained by physics. Gravity does not change between cultures. Stone hardness does not respect borders. Water behaves the same everywhere. Constraints guide innovation as much as creativity does. This helps explain why certain myths appear similar across cultures without implying direct contact. Flood stories arise wherever floods occur. Creation stories reflect shared human concerns. Stoneworking stories may reflect shared experiences of material behaviour. Some cultures tell stories of stones that soften, others of stones that move when sung to. These stories differ in detail, but they point toward the same observation. Stone responds under certain conditions. We should be careful not to literalize these stories or dismiss them outright. They may encode practical experiences in narrative form. Storytelling is a way to preserve knowledge without writing manuals. A story about singing to stone may not mean stone literally responds to music in a magical way. It may mean that rhythmic sound and coordinated effort made stone easier to work. Different cultures encode similar observations differently. The underlying experience is shared. There is also the question of social memory. Knowledge does not need to travel across oceans to echo. It can arise wherever similar conditions persist long enough. When societies transition away from stoneworking as a central activity, the knowledge fades, but the stone remains. Later observers, encountering similar stonework in different regions, assume connection because they underestimate convergence. Modern examples of convergence are easy to find. Pyramidal structures appear in many cultures because stacking material into a wide base and narrow top is stable. Arches appear independently because they distribute load efficiently. No one needs to teach another culture that an arch works. Stone teaches that. Precision fitting teaches similar lessons. Another overlooked aspect is that ancient builders often learned by repairing. They inherited structures built by earlier generations. When repairs were needed, they had to understand why something had failed and why something else had endured. Repair is a powerful teacher. It reveals stress paths. It exposes weaknesses. It encourages improvement. In regions where stone structures stood for centuries, builders had access to long-term performance data. They could see which methods worked. They could refine accordingly. This iterative process produces convergence even without contact. There is also the matter of scale of time. These methods did not appear overnight. They evolved over centuries. Small improvements accumulated. Poor methods were abandoned. Good ones persisted. From a modern perspective, looking backward, this appears as sudden sophistication. In reality, it was gradual refinement. Because the refinement was gradual, it did not feel revolutionary to those living it. There was no moment when someone announced a new technique. It was simply how things were done. This again reduces the likelihood of documentation. Another important point is that ancient builders often worked within sacred or ceremonial contexts. Building was not just functional. It carried social and symbolic weight. This encouraged care. Structures mattered, mistakes mattered, longevity mattered. When something matters deeply, people invest more time and attention. That investment produces quality. Across cultures, important structures receive the best craftsmanship. The echo we see may be partly due to shared human tendencies to prioritize what is sacred, but the techniques themselves remain grounded in physics. We should also consider the possibility that some similarities are exaggerated by modern selection. We tend to focus on the most impressive examples. Ordinary stonework varies widely. Exceptional stonework stands out. When we compare exceptional examples from different cultures, similarities become more apparent. Differences recede. This does not invalidate the pattern, but it reminds us to be cautious. Still, the consistency of certain features across continents suggests more than coincidence. It suggests that stone rewards certain approaches reliably. When people work with stone patiently, listen to feedback, allow gravity to act and prioritize fit, they arrive at similar outcomes. This is encouraging rather than mysterious. It suggests that ancient builders were not relying on fragile secret technologies that vanished. They were relying on robust principles that any attentive culture could rediscover. The tragedy is not that the knowledge was lost forever. It is that the conditions that supported its practice changed. Industrialization made time expensive and force cheap. That shift altered priorities. Techniques optimized for patience became obsolete economically, even if they remained effective structurally. As societies moved toward faster construction, the quiet methods were abandoned. But the echoes remain. They remain in stones that still fit, in walls that still stand, in joints that still hold after earthquakes. They also remain in traditional practices that survive at the margins: dry stone walling in rural areas, traditional masonry in isolated regions, craftspeople who still work slowly because they have learned that speed invites error. These living echoes are easy to dismiss as quaint or inefficient, but they preserve something valuable. Understanding that similar knowledge arose independently across distant lands reframes the entire question. We no longer need to ask who taught whom. We can ask what stone teaches everyone who listens long enough. This shifts the focus from lost civilizations to lost habits, from missing texts to missing patience. If these methods arose independently and quietly, how did later generations reinterpret them? At what point did explanation give way to legend? When practical knowledge fades, it doesn't usually disappear all at once. It drifts. It loosens from its original purpose and settles into stories, habits, and fragments of explanation that no longer quite match what they once described. Over time, what began as observation becomes metaphor. What began as method becomes legend. And when later generations look back, they often assume that the stories must have been invented to explain the stones, rather than the other way around. Legends about stone are everywhere. Stones that move on their own, stones that soften at certain times, stones that respond to sound, prayer, or song. In modern retellings, these accounts are often treated as symbolic at best, or fantastical at worst. They are grouped with myths about giants, gods, or supernatural builders, and then dismissed as evidence that ancient people did not understand their own achievements. But that dismissal may be too quick. Stories are one of the oldest tools humans have for preserving experience. Long before writing, stories carried knowledge across generations. Not precise instructions, but patterns. Not measurements, but relationships. A story does not tell you how to do something step by step. It tells you what matters, when to be careful, and what to pay attention to. When knowledge is embodied and situational, story is often a better container than text. Consider how many traditional practices are preserved through narrative rather than explanation. Farming calendars tied to mythic figures. Navigation knowledge encoded in songs. Ecological understanding embedded in origin stories. These are not literal accounts. They are memory aids. Stoneworking legends may serve a similar function. When a story says that stones were made to move by sound, it may not be claiming that sound alone lifted massive blocks into the air. It may be preserving the observation that rhythmic sound, coordinated effort, and vibration played a role in movement or shaping. When a story says stone softened, it may not mean liquefaction. It may mean that under certain conditions, stone became easier to work. The problem arises when later listeners interpret these stories literally, without the context that gave them meaning. Modern minds are trained to separate myth from technique. Ancient minds did not draw such sharp boundaries. A story could be meaningful without being mechanically explicit. It could encode practical constraints without explaining them. For example, a legend might insist that stone must be worked at a certain time, under certain conditions, with certain rituals observed. From a modern perspective, this looks superstitious. From a practical perspective, it may reflect environmental timing, temperature, moisture, seasonal stress in the stone. The ritual ensures compliance. You may not understand why it matters, but you follow the rule. Over generations, the rule persists even if the reason is forgotten. This pattern appears in many crafts. Fishermen follow taboos that align with ecological cycles. Farmers observe planting rituals that correspond to climate patterns. Builders observe ceremonies that mark transitions in work stages. The ceremony survives because it works. The explanation fades because it is no longer needed. In the context of stonework, legends may preserve instructions indirectly. They tell you to listen. They tell you to wait. They tell you to work together. They tell you that force alone is not enough. Another clue that legends may reflect real practices is their consistency. Across different cultures, stories about stone share recurring themes: sound, weight, cooperation, timing. Even when the details differ, the structure of the story remains familiar. This suggests that the stories are not arbitrary, they are shaped by experience. Take, for instance, accounts of stones that could not be moved until a chant was performed, or until everyone acted together. Read literally, this sounds magical. Read practically, it points to coordination, A chant synchronizes effort. It establishes rhythm. It ensures that force is applied smoothly and consistently. A stone moved chaotically resists. A stone moved rhythmically responds. The chant is not the cause in a physical sense. It is the organizing principle. Similarly, stories about stones that reject improper handling may reflect the reality that careless force leads to breakage. When a stone cracks unexpectedly, the explanation becomes moral or spiritual. The stone was offended. The ritual was not observed. This framing reinforces careful behaviour. Legends also preserve warnings. A story about a stone that crushes the careless teaches respect for weight and gravity. A story about a wall that collapses when rituals are ignored teaches attention to sequence and support. From a modern standpoint, these are cautionary tales. From an ancient standpoint, they are safety manuals. The difficulty arises when we treat legends as failed science rather than alternative knowledge systems. They were never intended to explain mechanisms in abstract terms. They were intended to guide behaviour. Another factor to consider is that ancient builders did not always see themselves as separate from their materials. In many cultures, stone is part of the living landscape. Mountains have identities. Quarries are sacred. Removing stone requires permission or ritual. This worldview encourages restraint. If stone is not inert, you do not treat it carelessly. You pay attention. You proceed slowly. Whether or not one accepts the worldview literally, its practical consequences are clear. Careful handling produces better results. Legends reinforce that care. It is also worth noting that stories are resilient. They survive conquest, migration, and cultural change more easily than technical instruction. Even when the practice disappears, the story can remain. Over time, the story may lose its original reference. What was once a reminder to work slowly becomes a tale about magic. What was once an instruction to coordinate becomes a myth about supernatural power. Later generations inherit the story without the skill. They marvel at the stones and assume the story explains how they were made. In reality, the story may be a shadow of the method, not its explanation. This inversion is common in archaeology. We assume myth was invented to justify architecture. It is just as plausible that architecture produced the myth. Another interesting aspect is that legends often emphasize collective action. Stones moved by many people acting as one, builders working in harmony. Individuals rarely appear as heroes in these stories. The group matters. This reflects the reality of stonework. Large stones are not moved by individuals. They are moved by coordinated groups. Emphasizing unity is practical. Legends that glorify cooperation reinforce social cohesion. They make the work possible. There is also the issue of authority. In some stories, only certain people can move the stones. Priests, elders, those with knowledge. This reinforces the idea that skill matters. It also protects the knowledge from misuse. Not everyone is encouraged to try. Again, this is not secrecy for secrecy's sake. It is risk management. When later observers encounter these legends stripped of their original context, they often conclude that ancient builders believed impossible things. But belief and practice are not the same. A story can be believed without being literally true. Its function is what matters. We should also consider how memory changes over time. As generations pass, details are lost. Explanations simplify. What was once a complex process becomes a single dramatic moment. A long, patient shaping process becomes a story about instant softening. A careful transport process becomes a story about stones flying. Compression is a feature of oral tradition. Modern listeners, accustomed to literal documentation, struggle with this compression. We take the story at face value and reject it because it seems implausible. But rejecting the story entirely may mean rejecting the clue it contains. There is also a tendency to separate rational and irrational thinking. Ancient people are often portrayed as either brilliant engineers or naive myth-makers. In reality, they were both practical and symbolic, often at the same time. Ritual and technique coexisted. They reinforced each other. A ritual that calms workers, synchronizes movement and marks transitions, improves safety and quality. Calling it irrational misses its function. Legends about stone may encode such rituals. Another point worth considering is that some legends describe failures as well as successes. Stones that could not be moved, walls that collapsed, builders punished for arrogance. These stories serve as warnings against overconfidence, against forcing outcomes, against ignoring limits. That aligns perfectly with the quiet knowledge we've been tracing. Stone does not forgive arrogance. It responds poorly to force. It rewards patience. Legends teach that lesson emotionally rather than technically. There is also the role of memory under stress. When a culture experiences collapse, invasion, or disruption, practical knowledge may be lost quickly, but stories persist because they are easier to remember and retell. After a collapse, people may remember that stones were once worked differently, but not how. The explanation shifts. What was once method becomes mystery. Later generations look back and assume that ancestors possess powers they do not. In some sense, that is true. But the power was not supernatural. It was practiced. This dynamic has occurred repeatedly throughout history. Roman concrete was forgotten. Medieval builders marvelled at Roman ruins and attributed them to giants or gods. In reality, the technique was simply lost. The same pattern may apply to ancient stonework. When legends speak of lost builders or golden ages, they may reflect periods when certain practices were widespread and later abandoned. Another interesting aspect is that legends often emphasize listening to gods, listening to the earth, listening to stone. This language may reflect the importance of sensory attention. Listening is a skill. It requires quiet. It requires patience. It requires humility. Modern environments are loud. Ancient work sites may have been quieter. Listening would have been easier. By framing listening as sacred, cultures reinforced its importance. This again ties back to vibration and sound. Stone communicates through sound. Listening reveals information. A legend that emphasizes listening may be preserving that insight. There is also the matter of repetition. Stories repeated across generations reinforce memory. Repetition also reinforces practice. A story told each time a stone is moved becomes part of the work. Over time, the story and the method become inseparable. When the method disappears, the story remains but loses its anchor. Modern interpretations often strip stories of their practical dimension. We analyse symbolism without asking what behaviour it supported. Reintroducing that question changes how we read these legends. It does not mean taking them literally. It means taking them seriously as cultural artifacts that may encode experience. This approach requires restraint. It is easy to project modern ideas onto ancient stories. It is easy to see what we want to see. The goal is not to prove that legends are historical records of specific techniques. The goal is to recognize that they may preserve fragments of real practice in distorted form, fragments that align with what we see in stone. When stories from different cultures emphasize similar themes, and those themes align with known physical principles, it is reasonable to ask whether they reflect shared experience rather than shared fantasy. Stone responds to vibration. Stone responds to water. Stone responds to weight and time. Stone rewards patience and coordination. Legends that emphasize sound, timing, and collective effort may be remembering that reality. When modern researchers approach ancient stonework, they usually do so with a problem-solving mindset shaped by contemporary tools. The question is often framed as how something could have been done, assuming that the answer must involve either unknown technology or extraordinary labour. But a quieter shift has been happening in the background, one that doesn't generate headlines or dramatic demonstrations. A small number of researchers, craftspeople and experimental archaeologists have begun to ask a different question. Not how could they have done this, but what happens if we try to work the way they might have worked. These experiments rarely look impressive at first glance. There are no massive machines, no explosive revelations. Progress is slow, results are incremental, but over time, patterns begin to appear, and those patterns align surprisingly well with the features we see in ancient stone. One of the earliest areas where modern experimentation has quietly changed assumptions is abrasion. For a long time, abrasion was acknowledged as a possibility, but often dismissed as impractical at scale. Rubbing stone against stone with sand in between sounded too slow to be meaningful. What many early critics underestimated was how effective abrasion becomes when pressure, repetition, and time are allowed to work together. In controlled experiments, researchers have shown that even very hard stone can be shaped predictably using simple abrasives, provided the process is continuous and patient. The key is not speed, but consistency. Material removal happens evenly. Stress is distributed. Cracks are rare. Surfaces evolve gradually, becoming smoother and more regular without dramatic tool marks. When two stone surfaces are rubbed together with fine abrasive under steady pressure, the high points wear down first. This naturally improves fit. Over time, the surfaces begin to mirror each other. No measuring is required. The process is self-correcting. This is not speculation. It is a standard industrial technique today known as lapping, used to produce extremely precise components. The only difference is that modern lapping uses machines to accelerate what gravity and patience can already do. When experimental archaeologists replicate this process without machines, using only weight and manual movement, they find that the results are not just adequate, they are remarkably precise. It takes time, but time is exactly what ancient builders had. Another area where modern experiments have begun to shift understanding is vibration. In recent decades, engineers have learned that vibration can dramatically reduce the force needed to cut or shape hard materials. Ultrasonic tools are now common in manufacturing. They work not by brute force, but by rapid oscillation that weakens material bonds locally. Ancient builders did not have ultrasonic generators, but they did have vibration, rhythmic tapping, coordinated movement, repeated rubbing. All of these generate oscillations. At lower frequencies, the effect is slower, but still present. Some modern experiments have explored what happens when stone is subjected to sustained rhythmic vibration while being abraded or pressed. The results suggest that vibration reduces friction, improves consistency of material removal, and allows finer control. The stone responds more predictably. The risk of sudden fracture decreases. What is striking is that these effects become noticeable even without high-frequency equipment. They simply require persistence. This aligns closely with ancient accounts that emphasize rhythm, coordination, and repetition. It also aligns with legends that frame sound as important, even if they do not explain why. Another rediscovery involves water. Modern stoneworkers often work dry for convenience, but controlled experiments show that working stone wet changes everything. Abrasives cut more evenly, heat dissipates, dust is reduced, surfaces become smoother with less effort. When water is introduced into abrasion experiments, material removal becomes more controllable. Microfractures are less likely to propagate. The stone behaves more cooperatively. This matches what we see in ancient stones that show smooth, refined surfaces without aggressive tool marks. It also supports the idea that repeated wetting and drying cycles may have been used intentionally to weaken surface bonds before shaping. Some modern experiments have also explored chemical interactions. Certain plant extracts and naturally occurring acids can etch stone surfaces slowly. This does not dissolve stone dramatically, but it does alter surface texture. When combined with abrasion, it can make shaping easier. These methods are slow, they require preparation, they require waiting, but they leave minimal trace once complete. This makes them difficult to detect archaeologically, but not implausible. Another area of rediscovery is placement under load. Modern builders often shape stones fully before placement. Ancient builders may not have done so. Some experiments suggest that placing stones roughly and then refining contact surfaces under load produces better fit with less risk. When stones are placed together and allowed to settle under their own weight, pressure reveals high points automatically. If abrasive is present, those points wear down. The process naturally converges towards stable contact. This explains why some ancient stones appear to have been adjusted after placement. It also explains why hidden surfaces are often as refined as visible ones. Modern experiments replicating this approach find that precision emerges not from careful measurement, but from allowing gravity to guide the process. Another rediscovery involves sequencing. Modern construction often isolates stages: quarrying, shaping, transport, placement. Ancient methods may have blended these stages. Shaping continued during transport. Adjustment continued during placement. Final fitting happened under load. When modern experiments adopt this blended approach, outcomes improve. Stones fit better. Errors are caught earlier. Stress distribution is more favourable. This again supports the idea that ancient builders were not following rigid plans, but responding dynamically. There are also experiments focused on sound as diagnostic rather than active force. Tapping stone and listening for tonal changes can reveal internal flaws. Modern acoustic testing uses advanced equipment to do this. Ancient builders did it by ear. Modern researchers who train themselves to listen report that they can detect cracks and weaknesses reliably after practice. This does not require exceptional hearing. It requires attention. This supports the idea that sound played a role in quality control rather than magical manipulation. Another rediscovered principle is restraint. Many modern attempts to replicate ancient stonework fail because too much force is applied too quickly. When researchers deliberately limit force and allow processes to unfold slowly, results improve. This seems obvious in hindsight, but it runs counter to modern instincts. We are accustomed to solving problems by increasing power. Ancient methods often solved problems by reducing it. There are also experiments involving coordinated human labour. Modern demonstrations often underestimate what groups of people can accomplish when properly synchronised. Moving heavy stones with surprisingly little effort becomes possible when force is applied smoothly and rhythmically. These demonstrations are not new, but they are often dismissed as requiring unrealistic conditions. In reality, ancient societies routinely organised large groups for communal labour. Coordination was not exceptional, it was normal. What modern experiments show is that coordinated labour is not just about strength, it is about timing. Stones respond differently to steady, rhythmic force than to sporadic pushing. This aligns with legends about collective action and ritualized movement. Another area of rediscovery is patience itself. Some experimental projects have deliberately stretched timelines, allowing weeks or months for processes that modern experiments usually compress into days. When time is allowed to act, subtle effects accumulate. Moisture penetrates, stress redistributes, surfaces settle, results improve. The difficulty is that such experiments are hard to fund, hard to publish, and hard to maintain. They do not produce immediate results, they do not fit well into modern research structures, and yet, the few that exist suggest that time was a central component of ancient technique. There is also growing interest in experimental archaeology that involves traditional craftspeople rather than engineers. Craftspeople bring a different mindset. They are comfortable with repetition. They pay attention to feel. They adjust intuitively. When such individuals work with stone using simple tools, their results often surprise researchers. Precision emerges not because they measure more, but because they feel more. This reinforces the idea that ancient stonework knowledge was embodied rather than conceptual. Modern experiments have also begun to reconsider assumptions about quarrying. Controlled splitting using wedges, water expansion, and thermal cycling produces clean breaks with minimal damage. These methods are slow but effective. Explosive quarrying, by contrast, introduces microfractures that compromise long-term durability. Ancient stones often lack such damage. This supports the idea that quarrying itself was part of the quality process. Another rediscovery involves tool material. Wooden and soft tools behave differently than hard ones. They deliver force gradually. They reduce shock. They encourage controlled shaping. Modern experiments using wooden mallets and stone abrasives find that the stone responds more predictably. Tool marks are minimal. Surfaces are easier to refine. These tools do not survive archaeologically, which explains their absence from the record. There is also renewed interest in the role of environment. Experiments conducted outdoors under variable conditions sometimes produce better results than those conducted in controlled indoor settings. Temperature, humidity, and natural light affect perception and material behaviour. Ancient builders worked outdoors. Their methods evolved under those conditions. Modern indoor experiments may miss this context. Another important realization emerging from modern experimentation is that no single technique explains everything. Ancient stonework likely relied on combinations: abrasion plus vibration, water plus weight, sound plus coordination. When modern experiments isolate variables too strictly, they miss interactions. When they allow interactions, results begin to resemble ancient outcomes. This complexity resists simple explanation, but it aligns with what we see in stone: complex fit, subtle shaping, no single signature. Modern experiments are also revealing that ancient results are not always as extreme as popular accounts suggest. Precision is often high, but not magical. Tolerances are impressive, but achievable with patience. This reframes the problem. Instead of asking how the impossible was achieved, we can ask how the difficult was made routine. That shift matters. It moves the conversation away from lost super technologies and toward lost habits. Perhaps the most important thing modern experiments are rediscovering is not a specific technique, but an attitude, an approach that values feedback over force, process over speed, fit over finish. When modern researchers adopt that attitude, results change. They stop asking how to replicate ancient stonework quickly. They ask how to let stone behave the way it wants to behave, and stone responds. The rediscoveries happening now are incomplete. They are scattered. They do not yet form a unified explanation, but they are consistent in one important way. They suggest that ancient stonework did not require knowledge beyond physical principles we already understand. It required attention to those principles over long periods. This is both reassuring and unsettling. Reassuring because it removes the need for speculation about impossible technologies. Unsettling because it implies that we have lost something, not because it was inaccessible, but because we stopped valuing it. Modern experiments are only beginning. Many questions remain open. Results are preliminary. Replication is limited. But the direction is clear. When modern people slow down, reduce force, listen to material feedback and allow time to act, stone begins to behave less like an obstacle and more like a partner. From here, the exploration naturally turns toward why this rediscovery is happening now and why it remains marginal rather than mainstream. What does it say about modern priorities that such methods feel novel rather than obvious? And what might be lost, not just in stoneworking, but in other domains when patience is no longer considered a tool? Knowledge rarely vanishes in a single moment. It does not usually end with fire, conquest, or catastrophe, even though those events make for dramatic explanations. More often, knowledge slips away gradually, unnoticed, because the conditions that once sustained it quietly change. What was once useful becomes inconvenient. What was once valued becomes inefficient, and eventually, what was once practiced simply stops being practiced, not because it failed, but because something else seemed easier. The knowledge behind ancient stoneworking appears to have followed this quieter path. At its core, this knowledge depended on time, attention, and continuity. It thrived in societies where long-term projects were normal, where labour was abundant, where energy was scarce, and where durability mattered more than speed. When those conditions shifted, the knowledge did not collapse. It became unnecessary. One of the most significant changes was economic. As societies grew more complex, the cost of time increased. Labour that could once be dedicated to slow, careful work became needed elsewhere. Trade expanded, populations grew, demands multiplied. Under these pressures, methods optimised for patience lost their advantage. Faster construction became more valuable than longer-lasting construction. This does not mean ancient builders suddenly forgot how to work stone. It means they made different choices. When iron tools became widespread, they allowed stone to be shaped more quickly. When mortar became common, it reduced the need for precise fit. When standardized blocks became practical, they simplified planning and reduced skilled labor requirements. Each of these changes made sense locally. Each solved an immediate problem, but each also reduced reliance on the quiet techniques that had once produced extraordinary results. Knowledge that is no longer needed does not get passed on. Another major factor was specialization. In earlier contexts, builders often learned multiple aspects of their craft: quarrying, shaping, fitting, placement. Knowledge flowed across stages. As societies industrialized, tasks became segmented. Quarry workers extracted, masons shaped, labourers placed, engineers planned. This separation improved efficiency but weakened feedback loops. Decisions made in one stage no longer reflected experience from another. The intimate relationship between hand, stone and structure was diluted. Once that relationship weakens, certain kinds of knowledge cannot survive. You cannot listen to stone if you never touch it directly. You cannot learn its behaviour if machines absorb the feedback. Mechanization plays a central role here. Machines are not just tools. They are filters. They remove sensation. They replace gradual force with concentrated energy. They make outcomes predictable, but they also make subtlety irrelevant. When a machine can cut stone quickly regardless of grain, moisture or vibration, there is no incentive to pay attention to those variables. The machine does not care, and over time, neither does the operator. This shift changes what skills are valued. Sensitivity becomes less important. Speed becomes more important. Precision is achieved through calibration rather than feel. Once this happens, embodied knowledge fades rapidly. There is also the matter of institutional memory. Ancient building projects often spanned generations. Knowledge was preserved through continuity. When that continuity breaks, knowledge evaporates. Wars, migrations, and social upheaval do contribute to loss, but not always dramatically. A single generation gap can be enough. If apprentices are not trained, if masters die without passing on skills, the chain breaks. And because the knowledge was not written down, there is nothing to recover later. This vulnerability is not unique to stoneworking. It applies to many traditional crafts. We see it today in the disappearance of hand-weaving techniques, traditional boat building, and agricultural practices. Once they are no longer economically competitive, they fade quickly. The difference with stoneworking is that the results remain visible. The stones endure. The knowledge does not. Another reason this knowledge slipped away is that it was never framed as knowledge in the modern sense. It was not theorized. It was not abstracted. It was not separated from practice. Modern societies tend to preserve what they can analyze, measure, and codify. Knowledge that resists abstraction is undervalued. It is seen as intuition, tradition, or habit, rather than expertise. As a result, when such knowledge disappears, it is not mourned, it is barely noticed. This is especially true when new methods appear superior. Iron tools cut faster than stone abrasives. Mortar allows quicker construction than fitted joints. Concrete simplifies everything. From a short-term perspective, these are improvements. From a long-term perspective, they represent a trade-off. Durability becomes negotiable. Maintenance becomes expected. Replacement becomes normal. Ancient structures were often built with the assumption that they would outlast their builders. Modern structures are often built with the assumption that they will be repaired, renovated, or replaced. This change in expectation alters how much effort is invested up front. Why spend years perfecting a stone fit if the building will be renovated in 50 years? Another factor is the rise of written authority. As engineering became formalized, written calculations replaced experiential judgment. This improved safety and predictability, but it also marginalized experiential knowledge that could not be easily expressed mathematically. Engineers are trained to trust models. Craftspeople are trained to trust feedback. When models work well enough, feedback becomes secondary. Over time, training systems adapt. New generations are taught what is valued. Skills that are not valued are not taught. Quiet, stoneworking knowledge did not disappear because it was disproven. It disappeared because it was unnecessary within new frameworks. There is also a cultural narrative at work. Progress is often framed as a story of improvement. Later methods are assumed to be better simply because they are newer. This narrative makes it difficult to acknowledge that something valuable might have been lost. Admitting loss complicates the story. It is easier to assume that ancient methods were crude and that modern methods represent refinement. Evidence to the contrary is treated as anomaly. This bias shapes research priorities. Few resources are devoted to understanding slow methods when faster ones dominate. Another subtle factor is liability. Modern construction operates under legal frameworks. Predictability matters. Methods must be standardized. Techniques that depend on individual judgment are risky in institutional contexts. Ancient stoneworking relied heavily on judgment. A master decided when a stone was ready. That decision was not easily transferable or defensible in a modern legal sense. Standardization reduces risk, but it also reduces nuance. Once systems prioritize risk reduction over craftsmanship, certain kinds of knowledge become incompatible. Education systems reinforce this. Modern training emphasizes theory and simulation. Practical exposure is limited. Apprenticeship models decline. Without long-term immersion, embodied skills cannot develop. Stoneworking at the level we are discussing requires years of direct contact. That is difficult to justify economically today. Another reason this knowledge slipped away is that it did not advertise itself. It produced results quietly. There were no dramatic breakthroughs, no inventions to patent, no moments to commemorate. History tends to remember moments. Quiet processes leave little narrative footprint. When historians reconstruct the past, they rely on texts, artifacts, and events. Techniques that leave no tools and no records are hard to place. As a result, the knowledge behind ancient stonework is often invisible to historical analysis. Even when scholars recognize the quality of ancient construction, they often attribute it to extraordinary labor rather than extraordinary method. Labor is easier to imagine than lost technique. This framing further obscures the knowledge itself. There is also the problem of modern replication bias. When modern attempts to replicate ancient stonework fail, the conclusion is often that ancient methods were impossible without advanced technology. This leads to speculation rather than an investigation. The possibility that modern attempts fail because modern priorities differ is less often considered. Modern experiments are often constrained by time limits, funding, and expectations of efficiency. Ancient methods do not fit those constraints. When results do not appear quickly, the experiment is abandoned. This creates a self-reinforcing cycle. Slow methods are underexplored because they are slow. They remain poorly understood because they are underexplored. Meanwhile, the stones themselves continue to exist, quietly contradicting assumptions. Another factor is that modern societies tend to externalize expertise. We trust institutions, certifications, and credentials. Ancient knowledge was often localized and personal. A master stoneworker's expertise lived with them. It was recognized by results, not by certification. When that person died, The expertise died unless it was passed on. There was no archive. This makes such knowledge fragile across time, even if it is robust within a living tradition. There is also the influence of colonial interpretation. Many ancient stone sites were first studied by outsiders who brought their own assumptions. They often underestimated local knowledge and overemphasized mystery. Rather than investigating indigenous methods seriously, they framed the work as inexplicable or primitive. This discouraged exploration of practical explanations. Once a narrative of mystery takes hold, it becomes self-perpetuating. It is more exciting to imagine lost civilizations and lost patience. The knowledge also slipped away because it was not universally applicable. It worked best under certain conditions, certain stones, certain climates, certain social structures. As societies urbanized and materials diversified, the conditions that favored these methods became rarer. Concrete, steel, and brick replaced stone as primary materials. Stoneworking became decorative rather than structural. When a material loses central importance, the knowledge surrounding it fades. This is not unique to stone. We see similar patterns with materials like wood in some regions, or earth construction. Knowledge follows materials. When materials change, knowledge shifts. Another subtle reason for loss is pride. Modern cultures often define themselves in opposition to the past. To acknowledge that ancient builders possessed refined knowledge challenges that identity. It suggests that progress is not linear, that something valuable can be lost. This is uncomfortable. It is easier to frame ancient skill as brute force or superstition than to accept that modern methods may have traded away something meaningful. There's also a psychological dimension. Slow work requires patience. Patience is increasingly rare in systems optimized for speed. Even when individuals recognize the value of slow methods, they may lack the institutional support to practice them. Knowledge that cannot be practiced cannot be preserved. This brings us back to the idea of slipping through fingers. There is no single moment when the knowledge was dropped. It simply became harder to hold. Each generation let go a little more. The irony is that much of this knowledge is not truly lost. It remains accessible in principle. The physical laws have not changed. Stone behaves the same way. Gravity still acts. Water still penetrates. What has changed is our willingness to align our methods with those realities. Modern experiments are rediscovering pieces of this knowledge not because it was hidden, but because someone slowed down enough to notice. This suggests that the loss was cultural rather than technical. As priorities shifted, so did attention. The knowledge slipped away not because it failed, but because it no longer fit, and yet the stones remain, continuing to demonstrate what is possible when time, attention, and material understanding align. They stand as quiet evidence of a different relationship to work. What lessons are still available, not as instructions but as examples? And what might it mean, in a modern context, to recover not the techniques themselves, but the values that made them possible? Stone does not hurry to explain itself. It never has. It remains where it is, holding the shape of choices made long ago, indifferent to whether those choices are understood, misunderstood, or ignored entirely. Long after the hands that shaped it are gone, long after the knowledge that guided those hands has faded, stone simply stays. That patience can feel like silence, but it isn't. It is an open invitation, one that has always been there, waiting for someone willing to look closely without rushing to an answer. When we say that stone is still waiting to be understood, we're not suggesting that it hides secrets out of spite or mystery. Stone is not withholding anything. It does not conceal knowledge deliberately. What it offers is visible, tangible, measurable. The difficulty lies not in access, but in approach. Stone responds poorly to impatience. It does not reveal much to those who demand quick explanations or dramatic revelations. It yields insight slowly to attention rather than force. Modern observers often approach ancient stonework with a sense of urgency. We want conclusions. We want to categorize, to label, to resolve. Was it done with tools or without? Was the method simple or advanced? Was the knowledge local or shared? These questions are not wrong, but they tend to frame stone as a problem to be solved rather than a record to be read. Stone is not a puzzle with a single missing piece. It is a surface shaped by thousands of small decisions, repeated consistently over long periods. Understanding it requires a similar mindset. Instead of asking what single technique explains everything, it may be more useful to ask what habits of attention shape these results. One of the reasons stone still waits is that it does not fit comfortably into modern narratives of progress. We like stories where knowledge accumulates neatly, where each generation builds clearly upon the last. Ancient stonework complicates that story. It suggests that some kinds of understanding can be refined, then abandoned not because they fail, but because they no longer align with changing priorities. That realization can feel unsettling. It implies that loss does not always come from ignorance or disaster. Sometimes it comes from success. When faster methods work well enough, slower ones are set aside. When energy becomes cheap, efficiency replaces care. Over time, what once mattered deeply becomes optional. Stone, however, continues to reflect the older priorities. It still bears the marks of patience, restraint, and feedback-based work. It still shows what happens when material is treated as something to cooperate with rather than dominate. Those marks do not disappear just because the mindset that produced them does. This creates a strange situation. We live among the results of a way of working we no longer practice. We can see the outcomes, but we struggle to imagine the process. That gap invites speculation. It also invites humility. One of the most important things stone still offers is a reminder that not all knowledge is explanatory. Some knowledge is relational. It exists only in the interaction between person and material. Remove one side of that relationship, and the knowledge collapses. Modern science excels at isolating variables. That strength becomes a weakness when dealing with systems that depend on integration. Ancient stoneworking was not a single variable problem. It was a system of interactions. Sound interacted with weight, water interacted with time, gravity interacted with shape, human coordination interacted with material response. Trying to isolate one element and declare it, the answer misses the nature of the process. Stone still waiting to be understood may really mean that stone still waits for a different kind of attention. Attention that is willing to sit with complexity without forcing simplification. Attention that values process as much as outcome. There is also an emotional dimension to this. Ancient stonework often evokes a sense of calm rather than awe when observed closely. The structures do not feel hurried. They do not feel strained. They feel settled. That quality is not accidental. It reflects the conditions under which they were made. When something is built slowly, with constant adjustment, the result carries that history. The stone remembers the absence of urgency. That memory is felt even if it is not consciously recognized. Modern construction often carries a different emotional signature. Speed leaves marks. Force leaves tension. Even when structures are impressive, they can feel brittle or temporary. Stone that has waited centuries without complaint feels different. This difference is part of what draws people back to ancient sites repeatedly. It is not just curiosity, it is recognition. Something in these structures resonates with a pace of life that feels increasingly rare. Understanding stone in this sense is not just a technical project, it is a cultural one. It requires asking why we find these structures meaningful, why we're drawn to their endurance, why their precision feels reassuring rather than oppressive. Those reactions are clues. They suggest that the values embedded in ancient stonework still matter, even if we no longer practice them widely. Stone still waiting to be understood also challenges the idea that understanding must lead to replication. We often assume that the goal of studying ancient methods is to recreate them exactly. but replication may not be the most important outcome. We may never rebuild on the same timelines. We may never return to the same economic conditions. We may never rely on stone in the same way. But we can still learn from the approach, the willingness to slow down when material demands it, the acceptance that not all problems benefit from speed, the recognition that feedback matters more than abstract plans. These lessons apply far beyond stone. Another reason stone still waits is that it resists ownership. You cannot patent gravity. You cannot copyright patience. The principles behind ancient stonework are not proprietary. They are available to anyone willing to adopt the constraints. This makes them easy to overlook in systems that reward novelty and exclusivity. Stone does not reward novelty. It rewards consistency. Modern culture often values innovation for its own sake. Ancient stonework reflects refinement rather than innovation. Methods improve slowly, through countless small corrections. There were no sudden breakthroughs to celebrate. That kind of progress does not fit well into modern storytelling. As a result, it is often invisible. Stone still waiting to be understood also reflects a mismatch between questions and answers. We often ask how ancient people achieved such results with so little technology. Stone answers by asking why we assume technology is the primary driver. Tools matter, but mindset matters more. A sharp blade does not guarantee precision. A powerful machine does not guarantee fit. Those outcomes depend on attention, sequence, and restraint. Ancient builders may not have had advanced tools, but they had advanced habits. Those habits are harder to recover than tools because they are not physical objects. They are patterns of behaviour reinforced over time. Modern experiments that rediscover aspects of ancient stonework often do so accidentally. Someone slows down, someone works without machines, someone pays attention to feedback, and suddenly results change. This suggests that stone is not waiting for new discoveries. It is waiting for old behaviours to be taken seriously again. There is also a misconception that understanding ancient stonework requires believing in extraordinary claims, that it demands acceptance of lost civilizations or unknown energies. In reality, understanding may require the opposite, letting go of the need for drama, accepting that remarkable results can come from unremarkable processes applied patiently. Stone does not care whether we find that explanation exciting. It simply demonstrates what works. Another aspect worth considering is that stone is indifferent to explanation. It does not change behaviour based on what we believe about it. It responds only to force, time, and condition. This makes it an honest teacher. If a method works, stone responds. If it does not, stone resists or fails. There is no placebo effect, no confirmation bias in the material itself. That honesty is valuable in a world where narratives often outrun evidence. Stone still waiting to be understood also invites a different relationship with uncertainty. We may never fully reconstruct every step ancient builders took. Some details may remain unknowable, but uncertainty does not invalidate understanding. It simply limits precision. We can still recognize patterns. We can still identify principles. We can still learn. Modern science sometimes struggles with this because it seeks completeness. Ancient craft was comfortable with partial knowledge. Builders did not need to know everything. They needed to know enough. Stone responded to enough. There is also an ethical dimension embedded in ancient stonework that we are only beginning to articulate. Building something intended to last requires accepting responsibility for the future. It requires thinking beyond immediate benefit. That ethic is visible in the care invested in structures that would never be finished within a single lifetime. Stone still waiting to be understood may be reminding us of that ethic. In a time when temporary solutions dominate, stone stands as evidence that permanence was once a priority. This does not mean ancient societies were perfect or sustainable in all respects, but it does mean that they sometimes invested deeply in things meant to endure. Understanding that choice may be as important as understanding the techniques. There is also the question of listening. Throughout this exploration, listening has appeared repeatedly. listening to sound, listening to feedback, listening to stone. Listening is not passive, it is active attention. Modern systems often prioritize output over input. Ancient stonework prioritized input. The stone spoke first, the builder responded. This reversal changes everything. Stone still waiting to be understood may be waiting for us to reverse that relationship again, at least occasionally. Not to abandon modern tools or methods, but to remember that not all problems benefit from domination. Some benefit from cooperation. As this long exploration reaches a point of rest rather than conclusion, it is worth noting that stone does not demand that we resolve every question. It does not require us to settle debates or choose between explanations. It simply remains available. The stones are still there, the joints still fit, the walls still stand. They do not argue for a particular narrative. They quietly demonstrate outcomes. Perhaps that is why they endure so well in a world full of noise. Understanding stone may ultimately be less about uncovering lost secrets, and more about recovering a way of paying attention. A way of working that values patience as a tool, feedback as guidance, and time as an ally. Stone is still waiting, not because it has more to reveal, but because we may not yet be ready to receive it on its terms. And that readiness does not arrive suddenly. It arrives slowly, through curiosity that does not rush, through observation that does not demand immediate reward. In that sense, the story does not really end here. It simply settles into a quieter pace, much like the processes that shaped the stone in the first place, leaving space for reflection rather than resolution, and allowing the material itself to remain the final, patient presence in the background.